Hi, welcome to this module in a series where we talk about the National Electrical Code and exam preparation. In this module, we're going to talk about derating DeMystified. Now, this is the application of where you take a conductor in a raceway or a cable assembly, and depending on the number of conductors that are in it or the ambient temperature of the area around it, you have to do something to the conductor because it changes the ampacity value that's given to us in the National Electrical Code. So in this episode, it's going to talk to you about the very basic principles of adjustment and corrections. We're going to talk about what really constitutes a neutral conductor, and we're going to, in order to be considered a current carrying conductor. We're going to talk to you about MC cable and AC cable and how to apply derating when you don't have to apply any derating. We're even going to talk about 31015B7, which is that little mini table that disappeared in the 2014 NEC, only to reappear again in the Informative Annexes D7 example, which was a kind of a little mini table on some applications for certain type of 1 and 2 family applications, multifamily, where you could actually have a smaller conductor than what you would get under 31015B16. That's a lot of information. We're going to cover all of those things. So let's get into it. Again, if you want to visit more about us on the web, go to masterthenec.com. But then you'll see in the ticker that's scrolling below, go to our website and you'll see links on there for YouTube, or go to youtube.com and then type in Master the NEC and subscribe to our videos and our educational series so you can learn more about the National Electrical Code. So let's get started in our presentation. First thing we want to talk about is step 1. We're going to talk about terminal limitations of conductor sizing. 110.14c is a temperature limitation. It states that the temperature ratings associated with an ampacity of a conductor shall be selected and coordinated so as not to exceed the lowest temperature rating of any corrected or any connected termination, conductor, or device. Conductors with a higher temperature rating than specified for terminations shall be permitted to be used for an ampacity adjustment and corrections in both. So what we're saying here is we're going to let you use a 90°C rated insulation, for example. As long as you meet the terminal limitations, we'll let you use a conductor for derating or ampacity adjustment and corrections as long as you follow the requirements of 110.14c. Assuming you follow all these rules, and you'll see those in a minute, those are going to be like the weakest limit or limitation that you're going to have to follow, because you can get insulation with a much higher rating. You could get other applications where the rating will be higher, but you're still going to be limited to your terminations. So let's not forget that. So as we start learning here, we want to make sure that we're putting all these pieces together. And the first piece is terminations. So let's look at terminations here. This is what we're talking about, the termination here. And this happens to be an overcurrent protective device, but we are talking about this termination based in this overcurrent device. This is its weakest component here. And it usually has a rating. It might be a 60/75°C. On a rare occasion, you'll get a circuit breaker that's rated for 100% of its use. And we'll talk about that a little later. But for the most part, it's going to be very much limited to whatever's marked on that actual lug termination. So you've got two rules here. You've got 110.14c1b and c1a. Now c1a is dealing with termination provisions where the circuits are rated 100 amperes or less, and the terminals are marked for 14 through 1 gauge. Then one of the following will apply. Okay, if you run into terminals or in an application where it's 100 amperes or less and they're not marked otherwise, or if they are marked 14 through 1 and nothing else is being considered, then you're going to consider the conductors for use here to be rated at 60°C. It's important that we read up here in the charging statement that it says, unless the equipment is listed and marked otherwise, conductor ampacities used in determining equipment termination provisions shall be based on table 31015B16 as appropriately modified by 31015B7. Now, B7 is that little mini table. 310.15B16 is our normal ampacity table, and we'll see that here shortly. So if your terminals are 14 through 1 gauge rated, or it's 100 amperes or less, you can assume that it's going to be a 60° rated conductor, and that's the ampacity you're going to choose from this table. However, item 2 says conductors with a higher temperature rating, provided that the ampacity of such conductor is determined based on the 60°C that conductor is used. So what we're saying here is that I can use the ampacity, the actual insulation value as say 90°C of a THHN, But because of its 14-to-1 conductors and nothing else is marked, or maybe it's an older piece of equipment I'm rewiring to it and there's no markings on it, but I know that I'm using a conductor that's 14-to-1 and the terminals maybe state that, or it's 100 amperes or less application, then I'm going to pull an ampacity from the 60-degree column. Okay. However, it's saying, look, if I have a conductor, well, we'll go back to the code. This is what I want, back to the presentation. Here's the point. On this one, it's saying, look, I'll let you use that higher temperature rating, provided that the ampacity of a conductor is determined based on 60. So if I want to use 90 degrees C rated insulation, that's fine. But because of these limitations up here, and I don't know any better, or the equipment's not marked otherwise, then I still have to be limited to 60 degrees C. Now, here's the one that me and you both use all the time. Usually the terminals are going to be rated for 75 degrees C, even in these sizes here, 14-through-1, or 100 ampere or less. The equipment is going to have a terminal and the lug is going to be rated 60/75 degrees C, so I'm able to use a 75 degrees C. However, I can use a 75 degree or even a 90 degree C rated conductor insulation. And conductors with a higher temperature rating, if the equipment is listed and identified for the use of such conductors, are perfectly acceptable to use. So that means that if it's 75 degree rated terminals, then I can use a 75 degree rated conductor on it, even though it might be terminals for conductors 14-through-1 or 100 amperes or less. Because of the markings on the equipment and it's 75 degree rated, then I can utilize the 75 degree column for that. But if I don't know otherwise, and this is the only thing that are given, then I have to assume it here at 60 degrees. And even if I use an insulation that's higher rating, because of what I've got here, I still would be limited to 60. Most of the equipment's going to be marked for a higher temperature rating, or it's going to be marked 75 degrees C, so usually I can just jump right into the 75 values. Item number 4 reminds us that for motors marked with design labels, letters B, C, and D, conductors having an insulation rating of 75 degrees C or higher shall be permitted to be used. Okay, so I don't have to stick to the C here. As long as the insulation rating is 75, I can use it, or even higher. At the end of the day, I'm going to have to make sure that I don't exceed the value in the 75 degree column. Even though I'm using a 90 for these motor aspects here, I'm still going to be limited to 75 degrees C ampacity values. Now, 110.14C1B is a little different. This is for terminal provisions where you have over 100 amperes, or the lugs are marked for larger than 1 gauge. And the 1 gauge here is American wire gauge. And when it starts getting up to like 250 kc mil and whatnot, all of those would be larger than 1. Now, those conductors are considered to be rated at 75 degrees C. Now, conductors with a higher temperature rating, like for example the 90 degrees C, provided the ampacity of the conductor does not exceed the 75 degrees C ampacity of the conductor, shall be used. Or up to their ampacity if the equipment is listed and identified for use with such conductors. Okay, so taking it back to me, is that I can use a 90 degrees C and apply my adjustment and corrections as long as I don't see the value that's in the 75 degrees C, because that's the terminal limitations. I'm perfectly okay. If the terminals happen to be rated for 90, and there's some cases where it might be, then I can use the 90 degree ratings. But if I'm not dealing with that and I've got a limitation on each end that might be limiting me to 75 degrees C, then that's the terminal I'm going to use. Even though I might use a 90 degree rated insulation, I'm still going to be limited to 75 degrees C. The most important thing to take away from here is that I can use the 90 degrees C value, and you'll see that later when we start looking at the tables. That ampacity value I can use for adjustment and corrections. Ultimately, I can't exceed the value given to us in the 75 degrees C or the 60 degree column, because I don't want to put that conductor in a volatile position based on its rating of its terminal. But I can use a higher rating of insulation in order to be able to adjust and correct from, and then I'll be okay. Now, let's talk a little bit about the load, because that was step 1, kind of talking about the actual terminal listings and everything like that. Let's talk about the load. Now, the first thing to remember is load is the load. All right, and I'll come back to me because I can kind of paraphrase this slide. The load is the load. If I have something in the code that tells me to take something at a continuous load, it doesn't change the load. The load is still the load. So I might have to size it based on the code or being used in 3 hours or more based on the definition in Article 100 for continuous loads. I might be able, and that's a maximum current for 3 hours or more. I might be able at that point say, well, what is the load? Well, the load is the load. It is, in this case, if it was 39 amps of a continuous load, the actual load is 39 amperes. Now, the code is telling me I have to size something, whether it's the overcurrent device or I have to compare two sizes for conductor sizing to consider the continuous load. But when we're talking about the load, just remember, the load is the load. That's going to be an important thing to remember when we start sizing conductors in 210.19a1b. Don't need to worry about that yet, but you got to remember that nothing changes the load. Now, the condition of use might affect it, but at the end of the day, the load is the load. Remember that. That's going to serve you well here in this module. All right, so the load may be a non-continuous load, a continuous load for whatever its intended use. For example, the National Electrical Code says that the load where the maximum, that's a key, maximum current in amperes is expected. It's not assumed to be, it's expected to be continuous for 3 hours or more is considered a continuous load. Okay, now the electrician has to use the NEC and knowledge of the load itself to determine its expected use. For example, luminaires in an office building will be expected to be on for 3 hours or more, day, night, what have you. Okay, it should be considered a continuous load. In some applications, even the National Electrical Code will actually tell you what's considered a continuous load, like for heaters or for motor applications. It'll tell you, take them at a continuous load. And so we have to remember that the load is the load, but there are other conditions that get applied onto that, whether it's a continuous use or whether it's something else that actually, or whether the code directly tells you that it's a continuous load that you have to take into effect. But don't forget, a load is just a load, okay? Now, understanding continuous load and how it affects devices and conductors is important to understand. There is a mandate by the NEC to account for continuous load at 125% of the actual load. And it does that by adding that additional 25% buffer on top of the actual load. In our case, 39 amps we've been talking about, or 35 amps, whatever one we want to do, that is the actual load. In order to calculate it for a continuous load, we would have to add an additional 25% buffer. So it's an easy thing to do is to take the actual load times 125% or 1.25, and now we actually will get the calculation that's being demanded on us by the code for continuous load. Okay. Now, this buffer above the actual load helps to ensure the installation system or the product's listing are not ignored, resulting in a potential failure of the product or even that product's installation type, which case could be THHN, XHHW, whatever it is. In our example here, we got a THHN/THWN-2. Now, traditionally, when we do calculations, as defined in branch circuits in 210.19a1, or if you're dealing with feeders in 215.2, okay, and of course 210.3 is overcurrent, you will begin to conductor sizing based on the largest conductor resulting from a comparison of 210.19a1a or 210.19a1b. I don't have the 19 here, but you get the picture. And again, if it's feeders, you generally mirror the same requirements in 215.2. I don't know why it's .3. .3 is the overcurrent requirement diagram. 215.2 is the same mirrored requirements that you'll see for conductor sizing for branch circuits in 210.19a1, A and B. Now, why is it important for the conductor? Now, the issue is less about the conductive material, that's the copper or the aluminum, being utilized. It's more about the limitations of the insulation system. Again, THHN, THWN-2, or XHHW, those are examples of conductor insulation systems that are evaluated under their respective UL standards. And GOR 83, for example, is what we use to evaluate THHN. It's a thermoplastic product. And UL 44 is what we use on XHHW-2 and RHH, RHW, USC, all these other ones. And actually USC-2 is also UL 854. But anyway, they're all like thermoset products, okay? So they're under UL 44. Now, in a perfect world where we didn't have more than 3 current carrying conductors in our raceways or cable systems, and that ambient temperature was not more than 86 degrees Fahrenheit or 30 degrees Celsius, then the actual ampacities that are found in 310.15b16 of the NEC would be the actual value that you pull from. that would be the actual value of what you'd go to. If you do your calculation, you go right there and you pull that value. Unfortunately, we don't live in a perfect world. We utilize more than 3 current carrying conductors in a raceway more often than not. And we also have an ambient temperature that usually is above 86 degrees Fahrenheit or 30 degrees Celsius. Because of that, the ampacity values that are on the table 31015B16, and we'll look at that in a second in case you're not familiar with it, those values are in that perfect world scenario. When they're not in that perfect world scenario, we still utilize them for the adjustment and corrections we're going to talk about today. But if there was a perfect world, we could pull it straight from that table. We don't live in that perfect world. So remember, if it's not 3 current carrying conductors or less, or perfectly 30 degrees Celsius or 86 degrees Fahrenheit, I'm still going to use this table, but I can't pull the values as they're given directly from the table. Because we've got conditions of use, ambient temperatures that are elevated, we've got number of conductors that are going to actually change the conditions of these conductors are exposed to, and we have to account for that. Now, if we just pulled the table 31015B16, and I want to show you the actual table so that we can do that in the code. So here's the actual 31015B16 right here. You're probably all very familiar with this. And in this table here, it's got the rules here, which tell you, again, not more than 3 current carrying conductors. This applies to raceways cables even buried in the earth. Still applies. And if the temperature is based on 30 degrees C or 86 Fahrenheit, any of these conditions aren't here, then these values aren't accurate, and you have to do something to them. Here's your 60, 75, and 90. Here's the type of insulation systems for each one of these conductors that are rated. Now, if you want to find out what these mean, like THHN, that's thermoplastic, high heat, and nylon covering, then you're going to go to 310.104A, and that's going to give you a complete list of all the different types of building wiring and what these numbers mean, what letters mean, and all that kind of thing. All right, so we got that. In our examples today, we're going to pretty much be primarily dealing with copper, and we're going to only deal with 18 through 1, and we're not going to talk about aluminum. Although remember that these rules would apply the same whether it was copper or aluminum, so don't lose sight of that. Okay. Also, a little tidbit in case you know, when you see a -2 on a product, that lets you know that it's okay for 90 degrees C in a wet or a dry location. Notice here that you have THWN. Well, I would only be good under 75 degrees C for the wet location because the W is for wet location. Okay, that 1H means 75 degree, 2 H's mean 90 degree. But in this case, this THWN would only be good for 75. And if I got to apply adjustment and correction, as we'll talk about later, I want to have that -2 on it because it allows me to use a 90 degree column. This one would only allow me to use a 75 degree column, and that could become a problem if I've got to apply some kind of adjustment that's going to end up lowering the ampacity that's given in this table. Okay. And here's our THHN that we're going to use for most of our examples for today, dry location application. All right, so what we did here is we just simply pulled out what's the more relevant terms here. We're using a 6-gauge insulations THHN, 90 degrees C rated, because that's what THH is in. HH is 90 degree. 1H would be 75. No H's would be 60. All right, so 6-gauge copper. We're dealing in copper. Under the 90 degree column is good for 75 amperes. Okay. Now, remembering we can't use a 90 for anything but adjustment and corrections unless all the lugs that are associated with the assembly are rated for 90, which you might have some lugs that stand by themselves that are not connected to a breaker that might be rated 90. And then if that's the case, you can use the 90 degree ampacity value. But in most cases, we're limited by circuit breakers or pieces of equipment that get evaluated, and they're going to limit the lugs to 60/75. Might even not even have 60 anymore. Most of them might be just 75. So this kind of gives you an idea what the ampacity. This is the actual maximum allowable ampacity for this 6-gauge under the condition of use, which is in a perfect scenario. Now, when we don't consider the terminations, because we already looked at terminations, and we're not going to roll those into the equation just yet. We want to say, look, we're simply looking at the ampacity. If we have no more than 3 current carrying conductors, and this one would be depict 75 amps. And the ambient temperature is no more than 86 degrees Fahrenheit or 30 degrees Celsius, then of course, that 75 is the maximum current in amperes that 6-gauge could carry continuously, forever, under the condition of use, and it would never exceed the temperature rating of 90 degrees C. Okay. If you want to see the definition of ampacity, you simply go to Article 100, and there's a definition of ampacity, and basically that's what it says. It says the ability to carry the maximum current in amperes continuously under the condition of use without exceeding its temperature rating. This is a perfect world. This is okay. A 6 can handle 75 amps. But we don't live in that perfect world. We routinely have more than 3 current conductors in the ambient, so much higher or hotter than 86 Fahrenheit or 30 degrees Celsius. So what happens when the conditions of use are not perfect? We have more than 3, and the ambient's higher or lower than 86 degrees Fahrenheit at 30 degrees Celsius. Well, we're going to show you later that we're going to have to compensate it by either lowering the ampacity or lowering the amount of current or increasing the conductor size. Okay, we got to do something so that we don't stress out that insulation. Okay. Now, when you have a continuous load, maximum current, and the definition of a continuous load is found in Article 100. It is the maximum current for 3 hours or more, and where it's mandated by the NEC. A multiplier of 125% is mandated when sizing overcurrent protection devices. Okay, so let me grab this back around. We looked at terminals. We looked at how we apply the different values for the 60 degree, 75 degree. We can use a 90 for adjustment and corrections. We have to really focus on the terminations. Now, and we looked at the load a little bit, so we understand that a load is a load. A continuous load is simply a value that we're putting onto it. And now we need to kind of tie that part together because we know terminals, and we'll wrap that up here at the end. Now we're looking at the load. A load is a load. Now let's talk overcurrent devices. Overcurrent devices are going to be sized at 100% of a continuous load, 125% of a continuous load and 100% of a non-continuous load. That's the rule, and it can't be any smaller than that. So let's look at what the rules say when we're sizing an overcurrent device. Because ultimately, when we size a conductor and we apply all these derating factors, we have to make sure that this new conductor that we have has an ampacity that can, 1, handle the actual load, and 2, can be protected by the overcurrent device. That's important. So we got to tie all those things together at the end. So let's look at the presentation a little bit more. Now, when we have a continuous load, again, the maximum current for 3 hours or more, or somewhere in the code mandates it, then we have to take a multiplier of 125%. However, it is important to understand that this only applies when continuous loads are involved. A circuit breaker or other overcurrent device can be sized at 100% of its rating for a non-continuous load. So a circuit breaker that's rated 20 amperes can handle 20 amperes indefinitely if it's a non-continuous load. Okay, the loads aren't the maximum current draw. They range up and down. It can go up to 20 amps. It can go down. It can go up. If it's a continuous load, then it's going to be limited to 125%. Now, the reciprocal of that is take the breaker, which would be a 20 amp breaker, multiply it by 80%, which is reciprocal of 125, and that's going to give us 16 amps. So continuous load can't exceed 16 amps, because if I took 16 amps times 125%, that's going to be the 20. So I can't exceed 80% of that breaker. That breaker has a limitation on it. Now, there are breakers out there that are designed for continuous use, and they would be listed at 100% of their use. That means I could take the continuous load of 20 amps and put continuously 20 amps on that breaker. But that's a special breaker that's actually listed and identified for that application. Standard breakers are not. They're generally going to be limited to 80%. And we're going to see why in a minute based on the UL standard for the circuit breakers. All right, so, but when it's a non-continuous load, again, I'll load that sucker up to 20 amps. If it, it doesn't stay on for continuously more than 3 hours, then it could be on for 20 amps for 2 hours, 59 minutes, 59 seconds, and 59 whatever it is. As long as it doesn't trip to the 3 hours, then it can be sized that way, and I'm not a problem with it. Now, there are breakers available. Like I said, they're rare, but they are out there that are rated for 100% use. And you are permitted to load those to the continuous rating all the way up to its full use. Again, if I have 20 amps of continuous load, and I can put it on a 20 amp breaker that is rated for 100% of its rated use. That would not be the case for a regular standard circuit breaker. Okay, now since we're on the subject of continuous use and how it affects circuit breakers, this is important to look at here. The circuit breakers are created and evaluated to carry 100% of the rated current for an indefinite period of time under normal conditions. In other words, you could load that thing up and it could run under test conditions. Now, those test conditions were under UL 489, and that is the standard for safety for molded case circuit breakers and circuit breaker enclosures. Now, this test actually included mounting the circuit breakers in a free air environment. In other words, they were suspended, they weren't in an enclosure, and they had an ambient temperature that was held at a constant 40 degrees C. This is approximately 104 degrees Fahrenheit. Okay, now under these test conditions, that molded case circuit breaker they're required to not trip at the rated current. Okay, so they have to stay engaged. Now, the heat that's generated by current flow, the lack of air circulation within an enclosure, and remember this test is done without it being in an enclosure, the additional ambient temperature can become a problem and the reliability of that circuit breaker's operation can be in jeopardy. So that general rule is, when you're dealing with continuous loads, is to take the actual load at 125%. And then that's what the rules in 210.20a says. And then, of course, you're going to go at that point to 240.6a and size the proper size circuit breaker. That's a little ahead, so we don't want to talk about that yet. Now, if you already knew the circuit breaker and you wanted to know what the maximum continuous load could be on that circuit breaker, just a standard circuit breaker, then I could take whatever the rating is of that circuit breaker, say the 20 amp breaker, and I'd multiply that 80%, and that's going to tell you that it can't be more than 16 amperes of continuous load. Okay, so that's the way you do it conversely. Now let's look at that in an example. So I have 50 amperes of continuous load. So I already know that. I've looked at it, or whatever my calculation is tells me I have 50 amps. So now I've got 50 amps of continuous load, or maybe my load is 50 amperes, but I have to take it as a continuous amps because something's on for 3 hours or more, or the code mandated it be considered continuous load, like for a water heater or a motor application. Okay, so I take the actual load, this is 50 amperes, times 125% or 1.25, depending on the calculator you're working with. And that results in 62.5 amperes. Now, the installer is going to say, okay, now I got to find a breaker that this goes on. So they're going to go to 240.6a, and they're going to look at the list of breakers, and they're going to see that there isn't one rated for 62.5. But they're going to be able to go and say, okay, 62.5 amps is because of the continuous loads at 210.10a demanded that overcurrent device be sized no less than 100% of the non-continuous and 125 of the continuous. Well, in our example, we only had continuous loads to deal with. We didn't have another non-continuous to add onto it. So we have to find a breaker. So since there isn't one that corresponds for 62.5 amps, and assuming we meet the rules of 240.4b, that's the next size up rule, the installer would select a 70 amp rated device. Now we can kind of look at that so you can see that there's no 62.5 rated device. Oh, we came back to me. We want to go to the code. And we're going to pull that out of the code. And let's see here. I was trying to do a search. Let's search for, we'll just go to it. It's easier to go to it. 240.6a. And we'll get down to it, and here we go. So here is 240.6a. And right here, we had to have a 62.5 amp, and we have a 60, but it said it can be no less than that. So I got to bump up to a 70, all right? So that would be my selected overcurrent protected device. Now, why is this important? You need to remember this, because at some point, we're going to do a calculation and we're going to determine what a new ampacity is of a conductor based on the ambient and the number of conductors. So we're going to get a new value. Ultimately, one of the last steps, and the reason I cover it as the first step, because we got to come back around and look at it at the end, you're going to compare now and see, well, this conductor's new ampacity, this is what my breaker has to be. This is what my conductor's ampacity has to be. Am I protecting that conductor at its ampacity? And the ultimate choice is I got to have an overcurrent device that's at least 125% of the continuous load, but it can't be any less than that. Is it going to protect this conductor? And it might result in me jumping up into a larger size conductor simply because I have to terminate it on this size overcurrent device because of the rules in 210.20a. Okay, so you've got to piece all those things together. All right, so we come back to the code, or to the PowerPoint. And the next size up rule we want to talk about. So it's okay to put the 70 on there. The code requires it. Now let's look at this rule here, 240.4b, and see when we can apply this next size up rule application, because that's real important that we know when we can apply it. So we're going to go to the code, and we're going to go back a little bit to this rule right here. And that is this rule here, and it is 240.4b. Now it's got 3 provisions here. Now this allows me, if it's 800 amperes or less, it lets me say, look, I can go to the next higher standard overcurrent device rating above the ampacity of the conductor, like what we did in our case, shall be permitted to be used provided all of the following conditions are met. Well, number 1 is the conductors being protected are not part of a branch circuit supplying more than one receptacle for cord and plug connected portable loads. Well, let me bring it back to me. This is going to be any duplex receptacle on a branch circuit where I'm going to have 2. If it's a single, I can get away with it, but I've got a duplex that has 2 receptacles. A duplex is 2. So if that's the case and I'm doing a branch circuit, I can't use the next size up rule if it's applying to a branch circuit that's supplying duplex receptacles. Okay, you know, it could be more than duplex, but that's just the minimum. 1 duplex would exceed this rule. If that's the case, I can't use the next size up rule. Okay, so I can't apply this next size up application, which gets you in a pickle, because if that rule was 62.5 and I can't use this next size up rule and the overcurrent device is required to be larger, I can't go down because it's got to be at least this size. So now it's going to result in a conductor that's going to have to probably be larger so that it can ultimately be terminated on that overcurrent device. So it gets into trouble. So you really want to be able to use this next size up rule. And we'll kind of cover all that here in a minute. So let's go back to the code. So the number 2 says, all right, look, I'll let you use this next size up rule as long as the overcurrent device isn't over 800 amperes. If the ampacity of conductors do not correspond with the standard ampere rating of the fuse or circuit breaker without overload trip adjustments above its rating, then I'll let you go to the next size up. Now, it also tells us, but that shall be permitted to have an other trip or rating adjustment higher. So I can use the next size up rule here as long as I have a standard ampere rated circuit breaker or fuse without an overload trip adjustment that actually goes above its rating. Okay, so if it goes above its actual rating, it's a 400 amp rating, and the overload adjust trip goes above that, or if it's an 800 amp and the overload adjust trip adjustment goes above that, then I cannot utilize this. Now, other adjustments can, but the overload trip adjustment cannot. So let's say, now this is very rare, just saying. Most of the time when you're dealing 800 amps or less, this is not going to be too much of an issue, okay? And the last one is just basically saying, look, the next higher standard rated selected does not actually exceed 800 amperes. So in this table, as long as the one that I'm choosing, if it was in between 7 and 800 and I'm choosing 800, as long as it doesn't go beyond 800, I'm perfectly fine. And any of the other ones that are in between underneath it are going to be fine as well. It's only when I start getting above 800 then I have the problem this provision doesn't work. Okay? All right, let's go back to the presentation. So let's say I meet all those rules, then the next size up rule pertains to me and I can utilize it. Okay? And that's why I was able to get from a 62.5 up to a 70 amp overcurrent device. Remember these rules for circuit breakers, okay? Or fuses. Actually, it's just rule for overcurrent devices. Now, remember now, if the load is non-continuous load, the 125% doesn't apply, and the circuit breaker, again, can handle 100% of the load. Remember, we talked about that earlier. We're only doing the 125% because it was a continuous load. If it's just a load and it's non-continuous, then I can size the circuit breaker to handle the load and don't have to worry about the additional 25% buffer on that. Okay? There is an exception to this rule for circuit breakers that, again, are rated at 100% continuous use, and we'll talk about that later. Basically, all that's saying is, in this example here, 50 amps is the actual load. It's a continuous load. I don't have to add the extra 25. If this breaker was rated for 100% of its continuous use, then then I could just size it. It could be a 50 amp, could handle a 50 amp continuous load. I don't need to worry about the 125. These breakers have to be listed as such. That'll have that marked on it, and you need to look for that. Otherwise, standard breakers, standard molded case circuit breakers aren't going to have that stamped on it. Now, remember when we said something about, let's talk a little about feeders. The same rule applies for branch circuits, but let's look at some feeder examples so we can kind of bring those in. If I have, remember the rule was for the circuit breaker, it said 100% of the non-continuous and 125% of the continuous load. That's what it says in 215.3 for feeders. And it kind of mirrors what it says in 210.20a. And it's in this case, we have a 50 amperes of continuous load, but we've added additional 65 amperes of non-continuous load. So what we've got is 50 times 125. Remember, we're sizing for the circuit breaker in this case. And then we have the 65 amps non-continuous at 100%, so it's 65. So you add the two together, you get 127.5, or rounded because 0.5 is a major fraction, a major portion. So we go up to 128 amps. Now, because it's a continuous load as defined in 215.3, again, the demand at the overcurrent device be not less than 100% of the non-continuous and 125 of the continuous. We've already done that. We've determined it here, and we've done that, and we're pretty used to that part by now. The code user looks at 240.6a like we just did a minute ago, and it looks for a circuit breaker that's 128 amperes. Well, there isn't one when they get there, and let's assume they're using the next size up rule again. Using that rule, the next size up would be 150. So if we looked at the code, we can verify that. 128 amperes would be right here because this is 125. It says it can't be less than that. So the next size up is 150. So 150 happens to be the size that we would select for our overcurrent device. Again, that's just another step. You put that away because that is the required overcurrent device for your application, depending on whatever values you're using. All right, let's come back. All right, now, so at this point, we've really only discussed how to size the circuit breaker in 215.3 for feeders, and of course, 210.20a for a branch circuit overcurrent devices. Okay, we've covered that. Now, let's look at that exception a little bit, because that exception can help out. Now, these are the same values we had before. Now, the exception says where the assembly, including the overcurrent device, remember, it's not just the breaker, it's the assembly to which this breaker is installed. That's going to be from the manufacturer. They're going to state this application. Obviously, if they put one of those special breakers in it, that they evaluate it with the assembly or the enclosure or whatever it's dealing with, the bus that it's connected to and all that. It says where the assembly, including the overcurrent device, is protecting the branch circuits, is listed for operation at 100% of its rating. The ampere rating of the overcurrent device shall be permitted to be not less than the sum of the continuous load plus the non-continuous load. Now, I'll have you know this applies the same whether it's a feeder or branch circuit, so don't worry about the statement there. So basically, it's able to take the 50 amperes of continuous and the 65 amperes are non-continuous, add them together, throw out that additional 25% because this is rated for use at 100% use of its rating. And if that's the case, it results in a 50 plus 65 is 115 amperes. Well, if that's the case, I simply go to the 240.6a as we just did, and I need to find a breaker that's good for 115. So when we do that, we go look, it's good for 115. Well, this is good for 110. That ain't going to work. It's got to be at least rated for 115. So here, a 125. So that would be the selection of our overcurrent protected device for our circuit. Again, that is only based on the variables that we've discussed so far. We haven't done any adjustment and corrections based on ambient and the number of conductors for adjustments. We're simply looking at terminal ratings based on what we've been presented so far. Keep it that simple. Don't get too far ahead of yourself. We've got terminations to worry about. We've got overcurrent devices to size to make sure we protect those conductors at their ampacity. Even at their new ampacity after adjustment and correction, we have to verify. We're just dealing with breakers now. But remember, when we start sizing it, we got to make sure that everything falls in place. Okay, I just like to start at the breaker and give you some clarification. All right, let's go back to the code, to the actual presentation here. Now, while this might result in a 125 versus a 150 from a standard breaker aspect, yes, it's a smaller breaker, but because this breaker is more than likely going to have to be, in order to achieve this, it's got to be 100% rated for its rated use, it's probably going to be more expensive. So it might be a wash, okay? Who knows? Because 150 amp breakers might be more readily available, and that's the standard breaker versus a continuous use type of rated for 100% of its operation. They might be more expensive. Not sure. Now, since we covered the basics of overcurrent protection, and we covered that for branch circuits and feeders, they were pretty much identical. We're going to move on now and start sizing conductors for the actual load. And when we do that, we've got two conditions we have to look at. We have a continuous condition for continuous use and then non-continuous use. And we have to look at how those variables. Also, if we have a continuous load, we're going to have to do the larger of the conductor resulting from a calculation between 210/19A1A and A1B. So here it is on the screen. And here's what the general rule says. Branch circuit conductors shall have an ampacity not less than the maximum load to be served. And again, remember, the load is the load. Now, conductors shall be sized to carry not less than the larger of the results of the calculation between 210.19A1A or B. Okay? Whichever results in a larger conductor, okay, is the one we're going to choose. Ultimately, one of the two is also going to result in the larger ampacity value as well, but that should take care of itself. So we have an A and we have a B. Now, let's do it this way. Let's make sure I make a couple things clear. Branch circuits. If the branch circuit we're dealing with has a continuous load, then we have to do the calculation based on 210.19A1A, which is basically going to take the continuous load at 125%, and any other non-continuous loads that might be associated at 100%. And then we're going to take it and go to column, the 75-degree column, if that's what our terminals are limited at, and we just simply pick a conductor from that column. We're not applying any adjustment and corrections here. We're just simply picking a column based on the values that are in 75 C, for example, if that's what our terminals are at. Now, we write that conductor down. The next thing we have to do, because a continuous load is involved, we have to also compare it to B. Now, 210.19A1B is going to tell us to take the actual load, whatever that load is, not worrying about the 25% for continuous load, just take the actual load. And we're going to multiply that or divide that. Well, actually, we're going to divide it because we're going to go up, because we want to ultimately pick a conductor in the 90-degree column that can handle the load after adjustment and corrections have been applied to it, and it doesn't breach the values that are given in the terminal limitations of 110.14C1. Okay, so we have to look at that. So we're going to examine that right now. So I just wanted to kind of, give us some, guidelines of where we're dealing at. So this is A, and this is B. And now A, we'll look at each one individually, but important, if the load is continuous load or a combination of both continuous and non-continuous loads, then you have to compare A versus B of these two here. And this is the same for a feeder, just incidentally, so don't get lost just because we're talking about branch circuits here. It has to be the larger of comparing A to B, and select the resulting largest conductor. However, if the load is 100% non-continuous, then you simply would go to B, and that would be your option here. Okay, and then you would apply your adjustment and corrections from the 90 C. It's permitted to do that. So let's look at A. Where the branch circuit supplies continuous loads or any combination of continuous and non-continuous loads, the minimum branch circuit conductor size can be larger than the minimum, but this says the minimum branch circuit conductor size shall have an allowable ampacity not less than the non-continuous load plus 125% of the continuous load. Okay? In our cases, we're just talking continuous load, then we just simply take the load times 1.25, and that is our non-continuous load. We go to 75 C column, if that's the terminals who we're dealing with, select the conductor that can handle that load, and then write that down, and write the ampacity and actually write down the conductor size. Then it says you do the same calculation as step 2 that we did for the overcurrent device. Like I said, you simply select the conductor size that can handle the load, keep in mind those terminals, go to the 75 C column, and pick your conductor. Again, not using the 90 C at this point. We're simply picking from the table. Now remember, 210.19a1a only applies if you have a continuous load or a combination of continuous and non-continuous load. If you don't have those, then you don't have to compare it to anything. You simply go to 210.19a1b for all non-continuous loads. So let's look at B. Now B is probably the one we use the most. It says, the minimum branch circuit conductor size shall have an allowable ampacity not less than the maximum load to be served after the application of any adjustment or correction factors. Okay, now let's come back to me again. Let's make it clear. The maximum load is the load. Okay, you're not taking the load at 125% and that's your maximum load. The load is the load. So if it's 39 amps, 35 amps, 60 amps, whatever, you might in 210.19a1a, you're applying 125% in order to do that calculation in the resulting conductor under the 75-degree column, if that's what your terminals are at. Under the B, you're simply taking the actual load itself, and you're making sure that after the application of any adjustment and corrections, that conductor can handle the maximum load to be applied. In this case, the load is the load. So don't get beyond that. There's a lot of people who do that wrong, and they want to take that 125%. So basically what you're doing is you're derating and derating. You're double derating. And that wouldn't be fair to the conductor size. It wouldn't be fair to the installation. It could result in a much larger conductor. Can you install larger conductors? Yes, as long as it fits the terminal. Okay, voltage drop, we do it all the time. There's other aspects under engineering design that we increase the size, but we always have to make sure that we're going to not violate those lugs. Lugs have a range, and you want to make sure the conductors that are going in it are within that range. Okay, so we make sure we don't violate that. All right, now so we have to do that. So now let's talk generally speaking when we're dealing with B. It says, well, with no exceptions applied, if we had 45 amp continuous load, then we had that buffer of 25%, then you would take the 45 amperes times 125%, which give you 156 amps. That's how we would do it for 45 amps if we had a continuous load, and that would be what we did in 210.19a1a. But we're in B. And B just says, look, take that maximum load to be served under the code rule, which is still the 45 amps in this little example here. The fact that it is taken as a continuous load in A doesn't change the fact that the actual load is being served, or even the maximum load to be served is no more than 45 amperes. So keep that in mind. Now, we understand what a load is. We determined how to put the pieces together for the conductors and using the tables. We have been talking largely, I guess, at this point about branch circuit conductors, but I just want to remind you that the rules for feeders for conductor sizing is found in 215.2. And there are a few exceptions in there that are different than what you get in 210.19a1a and B. So we do want to look at the exception. Now, this exception number 1 is an exception to the 125% rule that we just talked about in A1A. Now, notice this is for feeder, but here it says, okay, wait a minute. I know you take, let's come back to me because I want to make sure I set stage it right. So 215.2A1A is dealing with the same rules we had for branch circuits, means 125% of the continuous, 100% of the non-continuous. And that's how you size A. However, it says, wait a minute, I got 3 exceptions to that rule. Basically, the exceptions, the first one is going to say, well, let you get rid of that 25%. You're still going to compare the two, but I'm going to get rid of that 25%. Ultimately, it's going to probably equal the same as option B, but you got to do the calc. You got to be sure, right? So let's look back, and here's what the language says, and you're kind of already familiar with this because we've kind of discussed it. It says, if the assembly, including the overcurrent device, protecting the feeder, is listed for operation at 100% of its rating, you saw that earlier for the branch circuit application, it says the allowable ampacity of the feeder conductor shall be permitted to be not less than the sum of the continuous load plus the non-continuous load. So I can simply take, in this case, if it was a 50 amps of continuous load, if it was rated for 100% of its rating for its operation, then I could put 50 amps of continuous load on this 50 amp breaker. If it's a standard breaker and it's not rated for 100% of its rated use, then I would have to limit it to 80% of this value. Or I could take the 50 and I multiply it by 80%, and that's going to tell me what my maximum continuous load can be on this on the conductor for this breaker. Okay. Then we have an exception number 2. This is another exception to the A rule. It says, look, where a portion of the feeder is connected at both the supply and the load end to separately installed pressure connectors, as covered in 110.14c2, it shall be permitted to have the allowable ampacity not less than the sum of the continuous load plus the non-continuous load. No portion of a feeder installed under this provision of the exception shall extend into the enclosure containing either the feeder supply or the feeder load terminations, as covered in 110.14c1. Basically, it's saying you're not going to get away from those termination requirements at the overcurrent device or whatever the equipment is. But here's the rule. So take this one, for example. I have 500 kc mil here. There's 3 parallel sets. And over here, I have 600 kc mil. The code is stating, look, this part right here that you can't use, and this is the block it's talking about. Here are the pressure connectors in here. This portion here only has to handle 100% of the continuous load and the non-continuous load. In our example here, it's 1100 amperes. Whereas based on the actual load, we don't know what it is, we didn't do a calculation, but we're assuming it's 1200 amps. So in this case, because of these terminal limitations down here, and remember the rule, it says no portion of the feeder shall extend to the supply or the load portion that has the terminations, like in the equipment, that's going to have certain types of limitations, like circuit breakers. Then this size doesn't get that allowance. It's got to be sized, and it has to be 125% of the continuous and 100% of the non-continuous. Whereas here, I can result in a much smaller conductor. I would say much smaller. Difference between 500 and 600 is 100 kc mils. But that is quite a bit when you talk about this could be a certain length, and that could be a good cost savings to you. Remembering that you might have voltage drop involved, so you got to take all those things into consideration. You're still going to have your ambient adjustments, and you're going to still have everything else. But kind of taking into effect at least option A, it's saying, okay, don't worry about the extra 25% when you're doing this for this application. Now, I'll bring it back to me and just explain a couple things. A voltage drop is not a mandate by the code, except when you get into fire pumps and other types of applications where it specifically mandates it. Most of the time, it's an informational note. And under that informational note, it's not enforceable. However, it's a good design aspect that always should be considered, but I can't reject you for it. I can for fire pumps, and I could argue that a motor is not going to operate efficiently if you have a certain voltage. It falls outside of its operating parameter, but the code just doesn't say anything about that. We know that it could affect it and burn it up. You're going to be replacing them forever. So, voltage drop's got to be considered. But we increase conductor sizes for many, many things too, not just voltage drop. Engineer specifications and whatnot. Anyway, so here's the allowance in that application. Now, exception number 3 is reminding us, okay, grounded conductors that are not connected to overcurrent devices shall be permitted to be sized at 100% of the continuous and a non-continuous load. All right, well, because those terminations for the grounded conductor is not limited by a terminations issue, and generally the terminals itself might be 90 or whatnot, just the terminal. It's not on any device like an overcurrent device or a piece of equipment. Or an appliance, what have you. So you're usually going to be limited to 75 degrees C here. But it's saying when it comes to the grounded conductor, since it's not at one of these overcurrent devices, it's not a limiting factor is not attached to it. So I can just take it at 100%. I mean, the load is the load. I could take the 100% of the load, continuous load, and 100% of the non-continuous load, and I'd be perfectly fine. So that's an exception that allows you to do that for the grounded neutral conductor. Okay. Let's get back to the presentation. Now let's look at what makes these tables what they are. So 31015B tables, ampacities of conductors 0 to 2000 volts. That's what it covers. All of these tables that are in here have ampacity. For example, what we use the most is 31015B16, although there are other tables in here. For the scope of this presentation, we're going to talk about 31015B16 because that's the one that's most used by electricians and what's going to be used on exams. They're not going to utilize these, but the general rule applies. I mean, you could use these, and all this is saying is the tables here in 31015B1 through B7 could modify the values that are given in these ampacity tables. Just making you aware of that, that's all it's saying. And that's the kind of table setup. For example, when we're dealing with ambient temperature, it's actually 31015B3, and that falls between B1 and B7. But we also have 31015B, 3A is the number of conductors. B2A is the ambient, that falls in here. B5 is going to deal with the, I think that deals with the neutral conductor. B6 deals with the grounding and bonding type conductors that don't have to be counted and things like that. So anyway, this just shows you that all the tables correlate together. It also reminds us here again that the temperature correction and adjustment factors shall be permitted to be applied to the ampacity for the temperature rating of the conductor. So that's where you get this rule to say, look, why can't I use a 9 degree C for my adjustment and corrections? Because the rules in 31015B tell you that I can. Okay? Now, once it's corrected or adjusted, that ampacity, whatever it is of that conductor itself, after you do that, can exceed the ampacity values rated under the terminal limitations in 110.14c. And of course, we're always going to compare back to those terminal limitations to make sure that we are not going to exceed those ratings, just to make sure everything is good. Now again, the translation is the installer is permitted, not required, to use a 9 degree C installation system to apply those adjustment and corrections, such as the ambient temperature corrections other than 86 degrees Fahrenheit, 30 degrees Celsius, or when you have adjustments where there's more than 3 current carrying conductors, as the conditions of 31015B16 express. Then you know, obviously it's not a perfect world, so they're going to use these tables to be able to make an adjustment or correction, or basically apply our derating values. Now, in 31015B1, it kind of tells you what these type letters are. We kind of talked about that earlier. They're found in 31015B16. You see those. It'll tell you the different types of insulation systems. If you want to find out everything you need to know about these, then you're going to go to table 310104A and 310104B, and that's going to give you everything from the sizes these conductors can be manufactured in, whether it's a dry or wet location, what these acronyms mean. All these different things are going to be there for you to do that. Now, let's start looking at some conditions of use here. So first one we want to educate ourselves on is the ambient temperature correction factor. Now there is a formula, but the code says that I can use a formula or I can use a table. In our case, we're going to use a table, 31015B2A. Now there is 2 tables here. One is based on 30 degrees C and one's based on 40 degrees C. Since we're utilizing 31015B16, our ampacity table, that's based on a 30 degrees C, that's going to correlate with the use of this table, 31015B2A. So those are the 2 tables that we're going to deal with. Now, if I want to use a formula, I can, but a worst case scenario, and most of the inspectors aren't going to get into this formula, they're going to check and make sure that you're building it based on 31015B2A. And for our case in this program, we're going to use that. So here's a rendering of that table. And basically you can see you've got the insulation values here, temperature rating of the conductor, which results in the insulation value rating. Here's the ambience in Fahrenheit. Here's the ambience in Celsius. Okay, and it basically says the ambient temperatures other than 30 degrees C or 86 degrees Fahrenheit, you're going to end up coming over here and using this table. Okay, and you're going to have to make a correction here. The higher the heat, the less ampacity a conductor can carry. So you're going to have to adjust it to make sure that you don't put more ampacity on a conductor that could ultimately cause it to rise up and violate its temperature rating. You're trying to keep it down. Okay, so before I get into example, let me clarify. So we have an ampacity value and we add heat to it. So they add the heat to the conductor is going to heat up and it's going to get closer to that limitation of that insulation, let's say 90. So how do you adjust for that? You apply adjustment and corrections to it. You get a lower value on that you can use that conductor for. Now you make sure your load doesn't exceed this value, and this value can actually handle the load. You're actually moving the value down, but you still have the 9 degrees C based on what it is. So you're moving it down in order to build a bigger buffer between what the current is and what the potential heat could be as it gets up to the rating of the insulation, and you don't violate the rating. So you're building a little buffer. So we're lowering the ampacity in order to keep a protective distance between what the actual insulation rating is. So that's what we're doing. So that's why we're applying these various derating aspects. All right, let's go back to the presentation here. So let's look at our example. Let's do this one on a 35 amps. And this is non-continuous, pretty simple. It's 122 degrees Fahrenheit wherever it's being installed. Let's say it's inside a building, going through a boiler room or whatever, I don't know. But it's 122 degrees Fahrenheit. So we have 75 degrees C, 90 degrees C insulation. Terminals are 75. It's a dry location. Okay, so obviously these conditions don't mirror the conditions in 310.15b16 because there's more, the ambient here is 122. The ambient on that table is 86. So we already know we can't just pull a value from this table. We got to do something. Next, we know it's 75 degrees C terminals, and we know that we're using THHN, and it has an insulation that's good for 90. So again, under 110.14c1, as a smaller conductor, obviously it's going to be 14:1 gauge conductors here. But because of the terminals listed and everything's listed, I can use the 75 degrees C or even the 90 for adjustment and corrections, as long as I don't exceed the value in the 75. That's a lot of words to say what I'm going to do here. So I have to find a conductor first at 90 because we're doing an adjustment and correction. And then remember, there's no continuous loads here, so I only have to do based on 210.19a1b. So I take the 35 amperes and I divide it by 0.82, which is the value here. And that gives me 43 amperes. Now, I got this value because I went over to 310.15b2a, and it's because we're using 90-degree insulation. I was in this column, and I found my ambient, which was 122, and I just came together in the lines, and that was 0.82, and that is my percentage, and it's a decimal point, so it's 0.82. So now we have to go to 310.15b16. We have to find a conductor in the 90-degree column, because that's where adjusting and correcting from, because the code allows us to do that, for 43 amps. So here we've got, this is a depiction of a portion of 310.15b16. This obviously isn't the whole table, because on the other side of the real table, we've got aluminum values. And of course, the values here go all the way down to 2000 kc mil. But for our use, we're just taking a portion of it, and we're only dealing with copper in this example. So here's the general rules of the table. Again, we're dealing with not more than 3 current carrying conductors. That isn't a problem in our equation here. But we do have an ambient that is higher than 30 degrees C or 86 Fahrenheit. Okay, and ours was 122. So we have to deal with that. All right, so we find a conductor that can handle that 43 amperes. And it looks like we couldn't use a 10, but we can use a 5. I mean, excuse me, an 8. I don't know why I said 5 for, which is good for 55 amperes. Okay, so let's double check that to see after we apply the actual correction if it's still good enough to handle the load itself. And we take 55 amperes. Now we're coming down, so we do multiplication, and it's 55 times 0.82 equals 45 amperes. 45 ampere conductor now can handle 35 amps of maximum load. That is not a problem. And it doesn't violate the listing of the 75 degree C column. Doesn't violate that either. Okay, so we're good there. All right, so in this case, it would be an 8 gauge. We'd be good to go. Now, let's do the same one for a continuous load. Now, none of the other factors are going to change. In fact, the ambient temperature is still going to be 0.82 because we didn't change the 155 degree Fahrenheit. The only difference here is, if you remember earlier, I have to compare the larger of 210.19a1a versus 210.19a1b, right? That's what I have to do. So we already got the multiplier here, so we can move on. So here's what we're going to do. We take now we got to do A, and A says we take the 35 amperes times 125%, and that's 44 amperes. Now the only difference here, and you notice this is in red, but really when we're doing A, we now just come to the 75 degree column. And can an 8 gauge for 50 amps handle 44 amps? And the answer is yes, not a problem under this application here. So this conductor would be fine. Now we need to compare that, because we're dealing with a continuous load. We need to compare it with 210.19a1b. So we take the actual load, which is 35 amperes. Now we're going to divide again to go up, and ultimately it's going to do the same thing as we did over here generally. And again, remember that we're going to take the 35 amps divided by 0.82 equals 42.68. And because it's higher than 0.5, it's a major fraction, then we're going to do it and round it to 43 amperes. We got to find now, since we are adding a correction here, we get to use a 90. So under the 90, We come down, we find a conductor that's good for 43 amps. And you want the best option. Okay, you wouldn't arbitrarily come and choose 6. It might work, but for this application, we want to choose the best option. If you're taking an exam, that's what you're going to be expected to do. So we take the 55 amps. Now we want to check that to make sure again that it can handle the 35 amps. So we do the 55, which is what we had here, multiply it by 0.82 equals 45 amps. And obviously 45 amp conductor now can handle 35 amps of load. That's the maximum load. And it doesn't violate the listings from the 75-degree terminal rating. So we're good to go there. Now this is basically what we did here. And the first calculation resulted in an 8 gauge because we did it at 35 at 125%, 50 amps. It was an 8 gauge we took from the 75 column. And then down here we did the same thing as we just did. All the steps. We did the 55 amps because that was the 8 because we did this one here, the 35 divided by 0.82, 43. We went to the 9-degree column. We chose an 8 gauge, good for 55 amps. Now we want to validate that. Again, 55 times 0.82 gets 45 amps. Again, that can handle 35 amps of actual load, no problem. And it doesn't violate the 75-degree terminal listings. So ultimately, both of these conductors ultimately were the same, right? But it's going to result in an 8 gauge wire, okay? Now let's talk a little bit about adjustment factors. We've talked about ambient corrections, but now let's talk adjustments. So any application where we have more than 3 current carrying conductors in a raceway or cable, or we have single conductors or multi-conductor cables installed without maintaining spacing for a continuous length longer than 24 inches, and those that are not installed in raceways, and that would be like MC cables, tray cables, whatever is installed in what we call bundling, where they're tied together in spaces longer than 24 inches, then we're going to have to apply some type of adjustment here, okay? Now, the allowable ampacity of each conductor that's based in 31015B16 is going to actually be reduced by the values that are provided in 31015B3A, okay? Now, this rule continued to remind us that current carrying conductors of a parallel set of conductors shall be counted as current carrying conductors. And you're not going to count the conductors that are not under 210, 215, 220, and 230. In other words, signaling and control, you don't count those as current carrying conductors. So let's kind of give a synopsis of what we're talking about, an overview. If I have like that picture I showed earlier where I have 3 raceways and it's a parallel installation, all of the conductors, the current carrying conductors that are in the raceways, all of them in that raceway are going to be considered current carrying conductors. And in some cases, even a grounded neutral conductor where it's a 4-wire 3-phase and 2 wires and a neutral are coming off, or three wires of a 4-wire Y system, then that neutral conductor is going to carry approximately the same amount on that neutral, so you're going to count it as a current carrying conductor. Now, even if I have a 4-wire 3-phase Y system where I have a lot of nonlinear loads, then also you're going to have harmonics and you're going to count that neutral as a current carrying conductor as well. So just keep that in mind how you count it. And we're going to cover that in the presentation, but I just want to kind of throw that out there. Hopefully that's not way over anybody's head at that point. We're just kind of just laying some groundwork is all we're doing. All right. Now here's a depiction of that table. Now this is 31015B3A, and I've added some language here in order to add clarity to the table. But let's say I have more than 3 current carrying conductors, or I'm bundling as we talked about earlier. Then it says when you bundle conductors together in a raceway or cable assembly, or even individual conductors as expressed in 31015B3A, that was the in single conductors or actually what was it? Single conductors. I don't remember what I said here. Where it said single conductors or multi-conductor cables, there we go, are installed without maintaining that spacing. And actually, at that point, then in 24 inches or more, then at that point, we're going to have to apply some kind of adjustment to that, okay? So, because of mutual heating that takes place, because you got all these conductors in this bundled raceway, or all these conductors grouped together, or all these cables that are running too close together and they're strapped together on the same bridle ring or whatever, then it's going to be hard for them to dissipate heat. So to compensate for that increased heat from the mutual contribution of other conductors or other cables, you're actually going to lower the conductor's allowable ampacity, and that's why we apply all these derating applications. Okay. And also remember that in this table, if you're looking at it, it'll say 80%, 70%, 50%. And of course, it says percent of value. You want to remember that you want to convert this to a decimal because it's easier for your math. So I just did it here already, but it's simply go to the right of the 0 and go 2 spaces to the left with your decimal point, and that converts it to an actual decimal. And that's basically easy for calculations. Notice how this says 4 to 6. So again, this is for those applications that are more than 3 current carrying conductors, okay? So that's what this table applies to. And there is some notes down here, and we'll talk about those notes here in a second. Now this is a kind of a depiction of mutual heating. So these individual conductors are in this raceway. We're not doing a raceway field calculation, of course. That's why it's not to scale. All we want to say that is under load, each one of these conductors are putting off actual heat. And you're getting mutual contribution from the conductor that's right next to it. Of course, you're getting radiated mutual contribution from the raceway that encompasses it. Now, normally with raceway field, we're going to have a pretty good space inside of here, and you can't exceed it, whether it's 31%, 40%, 53%, whatever it is based on the number of conductors that are in here and what have you. But in this depiction, we really just want to show you that these conductors actually give off heat, and they actually can play off of the other conductor. And it makes it very hard for a conductor to dissipate its heat inside of an enclosed space like this. So this one kind of gives you the picture of the table in the National Electrical Code. I like to at least throw one of those in there. This is directly out of the code, and it comes from edition that I actually have rights to. So here it's table 31015B3A. I'm going to give you an abbreviated version like I did previously. But let's do a little calculation here. So what is our situation? We have 35 amperes of non-continuous load. And we have 6 THHNs, copper conductors, in a dry location with the terminals are 75 degrees C. It's in an EMT. All right, so you notice we're not talking any ambient right here. We're simply talking adjustments. So everything else would be generally the same as we did for the ambient correction. 35 amps, 6 conductors, okay. 75 degree terminals, okay. 9 degree insulation, we're good to go. I go over to table 31015B3A, which is this here. I determine I've got 6 current carrying conductors, so I got 4 to 6. I come over, and I'm going to have a percentage of 80% or 0.80. All right, so that's what we got here. Now, the actual load is 35 amperes, but since this is a non-continuous load, I didn't have to worry about taking anything into continuous load. I didn't have to worry about 210.19A1A. I could simply go to the B, and I do this. I go 35 amps, and I'm on a division in order to tell me what conductor I have to choose from the 9-degree column that after adjustment and corrections is at least going to handle this load. So I take 35 amps and divide it by 0.80, and that's 43.75 or 44 amps. Because it's 0.7, I can round up. Okay, so it's 44 amperes. So now let's pick a conductor. So 44 amperes, I need a conductor. So here we go. I'm not going to work on a 10. So it looks like an 8 is good for 55 amperes. So, and it's THHN, it's 9 degrees C, so it looks like I'm good. Amps. Now, I looked in the 9 degrees C, I saw an 8 gauge, and that appears that that's what my conductor is, and it can still handle the load after the actual correction. Now let's verify that. 55 amps, that's this value here. 55 times 0.80, that's the 80% due to the 6 current carrying conductors that are in the raceway, which was an EMT. That equals 44 amperes. So my new value is good for 44 amperes. I now compare it to the 75 degrees C. It doesn't exceed the 75 degrees C value, so it's perfectly acceptable to be an 8 gauge. And so that's what my conductor size would be. Now the same situation, we want to do this one. We'll do the continuous load. You'll see the steps are still the same. All the variables are still the same. We take 35 amperes and we divide it by 0.80. Again, it gives us 44 amperes. However, the difference here is now, since it's a continuous load, you might remember we have to compare it to the largest ultimate conductor in accordance with 210.19A1A or 210.19A1B. And whatever conductor results at the largest conductor, that's the one we're going to select. Okay, so let's go back to that. All right, so we're solving the problem here. And so we knew we had 44 amperes. And under A, we do, okay, this was B. So we know what we got to do here. We've already compared the two. So let's just go to the actual calculation. So here's what we got to do. We got to compare the two. So the actual load is 35 amps, and A says we got to do it at 125% because it was a continuous load. So that is 44 amperes. We go to the 75-degree column, and we choose a conductor, and it was 8 gauge. We're good to go. It's ready for 50 degrees under that column. 50 amperes under that column. Now, 210.19A1B is the other method. Since it is a continuous load, we have to compare the two. So we take the actual load, 35 amps, divided by 0.80. It gives you 44 amps. They're identical here in this case. I go to the 90-degree C column. I choose a conductor. Obviously, a 8 gauge can handle 55 amperes. We verify that by going 55 times 0.80. That equals 44 amperes. Can that handle the 35 amps of maximum load? Yes, it can. It doesn't exceed the rating on the 75-degree C terminal. We're good to go. So ultimately, what we've got is an 8 gauge conductor, and that's the size that we want to utilize. Now let's talk about this little note under here, because we need to cover what the note is. Now the note is telling us that, look, see that little one right there? It says when you're counting the number of conductors in a raceway or cable, you also count any spare conductors that could potentially be used as current carrying conductors, even if they are only being used at this time as a spare in that installation, because at some point somebody can use them. And then chances are they're going to use it for a current carrying conductor. They're not going to use it as a neutral or a grounding or anything like that. So the inspector is required to consider it to be a current carrying conductor when you're doing that count. Okay. Now, the also note reminds the installer that you don't have to include any conductors that are connected to electrical components that cannot be simultaneously energized at the same time. So what example would that be? Well, use a three-way switch is the easiest way. You have a common terminal and you have travel terminals. You want to turn on a luminaire from two locations. So the conductors come in, the circuit conductors come in. The hot conductor or the ungrounded goes to the common terminal, supplying power to the switch. And then you've got a little switch in there that switches back and forth to the actual traveler terminals. So at any given time, current is traveling on one of those travelers, but it's not traveling on both of them at the same time. So if I was doing that, I get to discount one of them and only take one of the conductors as a current carrying conductor for this application, because it's impossible for current to travel on both of those conductors at any given time. So where you have equipment that utilizes this application, then you're able to use this rule here for that. Okay? And that's what the note actually is referring to there. The last two we want to talk about is 310.15B5 and B6, because both of those are encompassed here as well in this note, so we want to talk about those. So we were talking about this a little earlier, and this is what's considered a neutral conductor and whether or not you have to count it as a current carrying conductor. Well, this is pretty simple to understand. A neutral conductor that carries only the unbalanced current from the conductors of the same circuit shall not be required to be counted when applying the revisions of 310.15B3A. So this is a typical, let's say, residential transformer from a pole. It's dropping down. You have two hot conductors, leg A, leg B, and you have a grounded neutral conductor. It carries the imbalance between these two phase conductors. So it does not have to get counted. Now, in a multi-wire branch circuit, if you install that multi-wire branch circuit correctly, and that's important, if you don't know what a multi-wire branch circuit is, then this isn't the video, or you maybe need to go back into our basic video. But let's say you have a multi-wire branch circuit where you're using a 2-pole breaker or 2 individual circuit breakers with an identified handle tie that keeps them right next to each other, so that ultimately the breaker's on 2 different legs within the panel. And you use a multi-wire branch circuit, let's say a 12-3 or 12-2, and you're sharing a neutral. Based on the cancellation effect that takes place, that neutral will carry the imbalanced load between leg A and leg B. And it means that you won't overload that neutral. And since it carries the imbalance of the load, it doesn't have to be considered as a current carrying conductor. However, that is not always the case. That's just an example of where that might come into play, and you don't have to count the neutral. All right. But there are 2 applications where that is not the case. And here's the first one. In item B, it says a 3-wire circuit that consists of 2 phase conductors and a neutral conductor of a 4-wire, 3-phase Y-connected system. The common conductor carries approximately the same current in the line as the line to load currents of the other conductors and shall be counted when applying the provisions of 310.15b3a. So here's a Y, and you see they're only deriving from this Y 2 phase conductors and 1 neutral conductor. Well, if that's the case, because it's not taking this, you're not going to get a cancellation effect. And what happens is the imbalanced load that could be put on this neutral could actually be approximately the same amount of current that's traveling in these. Okay, vectorially, and hard to show that in a graphic, and I didn't prepare one, but it actually is if you're grabbing here and you're grabbing here and you're pulling both of these in this direction. That means ultimately the neutral could potentially is moving in that same direction, and it can actually carry approximately the same current as these other ones. Again, that is a simplistic description, probably not 100% accurate, but I think you get the idea. Just remember it if you're dealing with one of these type of systems. And then C says, okay, wait a minute. If you're dealing with a 4-wire 3-phase Y circuit where the major portion of the load that's placed on the circuit consists of nonlinear loads, harmonic currents will be present in the neutral conductor. The neutral, therefore, shall be considered current carrying conductor. All right, so let's talk about nonlinear loads for a second. So what is a nonlinear load? If I just had to tell you what one is, a nonlinear load would be fluorescent lighting in a building. Would be a variable frequency drive systems. Those are examples of nonlinear loads. So an example of a linear load would be like a motor, okay? If I give you a graphic to kind of talk about what harmonic currents are and how they can distort the waveform, let's say we have a bucket of water, and the sides of the wall of the bucket, okay, is the harmonics, okay, distortion. And what happens is I drop a rock in the water. So it creates these waves, and they pattern out from the waves. And these waves are symmetrical. They're perfectly sinusoidal. They move continuously out until they hit the wall. They hit this nonlinear load. This nonlinear load all of a sudden now creates harmonics. The harmonics represent that reverberation of those waves. If you drop in a bucket and it goes out, you'll see that it'll hit the ends and it'll start coming back. It's the perfect sinusoidal waveform that actually gets distorted because the waveform that comes back disrupts that waveform, and it goes from being a perfect waveform that has a good cancellation effect, turns into a position where it doesn't cancel current that's traveling on a neutral, and that neutral could sometimes carry twice the amount of current on it than any of the phase conductors. So you have to end up, if you've got these situations where you have higher harmonics, you have to have a K-factor transformer. You might have to oversize the neutral because that neutral is going to have a lot of current flowing on it. Well, obviously, you're going to count that conductor as current carrying because that example. Now, that example, the bucket, now that's an oversimplistic value of it, but that's what happens. You don't have a perfect waveform. It gets all distorted, all fragmented. And it's hard to have cancellations of loads on a neutral when you don't have a perfect, when that neutral is carrying an imbalance, because it's not. It's carrying so many values that aren't canceling out, and that neutral could end up being overloaded. So you have to take that in consideration. That's another example why you might see some neutrals inside of a panel of a 3-phase system like that with high harmonics, where you have the neutrals that were white end up turning gray or grayer or brown or whatnot. It's because the current that's traveling on that grounded neutral conductor is exceeding its rating, and you might need to check that. It's starting to damage the insulation, so keep that in mind. All right, so let's see here. Now, let's talk about 310.15b6, because we just talked about B5. Now, 310.15b6 is pretty simple to look at. Basically, it's saying, look, grounded and bonding conductors, the grounding and bonding conductors, you don't count those when you're counting the provisions of 310.15b3a because they're not current carrying conductors. They're bonding and grounding conductors, so I don't have to account for those. While we're here, we also might as well look at 310.15b4, which is giving us some direction on bare and covered conductors. And again, we want to understand what they're talking about here. And it's reminding us that, look, if you're dealing with a bare or covered conductor, are installed within you're installing them with insulated conductors. And again, 250.118a is going to allow us to use bare, covered, or insulated equipment grounds and things like that. So, you know, it's not necessarily required to be insulated. Now, there's some applications like for 517 healthcare facilities where you're going to have insulated conductors or equipment grounds that are insulated and what have you. But just as a general rule, the code allows them to be bare, covered, or insulated. All right, so it's just reminding you that the temperature rating of the bare or covered, now I can see where it might apply to the covered, but the bare is kind of difficult to have any kind of rating for that, shall be equal to the lowest temperature rating of the insulated conductors for the purpose of determining ampacity. Okay, well, I don't think we have to worry so much about the bare. We do have to look at the covered if it's used, and the covered has to make sure that it has adequate values based on the lowest temperature rating of whatever the other insulated conductors are in the rating, in the raceway or cable. Probably going to be 90 if we're doing adjustment and correction, so need to make sure it's equivalent to that. As far as the bare, it's interesting enough. I do get people that ask me, what is the UL listing for bare copper? And that's not a UL, it's an ASTM standard. Okay, and that ASTM standard, whether it's B3 or B8 or what have you, that discusses the soft drawn, hard drawn, whatever copper, the number of strands, stranding in B8. That's what covers all the stranding. Now, once you take it and you insulate it, then you're utilizing standards like UL83 and UL44, which is a UL standard that talks about how thick that insulation has to be and what type of testing that those conductors have to be exposed to make sure that they don't fail under the use, under the test parameters. That's different. But ASTM is what we use when we're dealing with copper. So, kind of deal with that. So it's kind of good information to throw out to you. Now let's talk about rooftops. Now 310.15b3a used to be more complex in the 2014 code. It's simplified a little bit here in the 2017 code. Basically, I'm going to paraphrase for you. If you have a raceway on top of a roof, it's subject to direct sunlight, and it is 7/8 of an inch or higher, then you only have to do an ambient correction. Okay, we have to do that anyway. We have to know what the temperature is in the environment, just like we've already learned how to do an ambient correction calculation. So it applies here. So if the raceway is outside in direct sunlight above the roof and whatnot, then it's still got an ambient temperature. And you can find these ambients for any given place in the country by going to the ASHRAE Handbook of Fundamentals. Now, the ASHRAE Handbook of Fundamentals, you probably have to pay for it. And basically, that gives the values for the 3 worst months, the peak months of a year, whereas the temperatures are going to probably be the hottest, and you have to use that value. Now, we use that anywhere except for inside of a building when we have to look at the condition of the building, whether it's a boiler room, and then we choose our ambient temperature. But when you're outside, you're going to use this table. Now, if you don't want to go and get the ASHRAE Handbook Fundamentals, then you can just go to copper.org. That's copper.org. And when you go there, go to the search feature and type in rooftops. If you type in rooftops, you're going to be taken to a location that's going to give you a nice little PDF download that you can put on your truck, keep in your code book. And that's going to give you that 2% design factor for the ambience for 3-month periods. Usually it's going to be July, August, and September, or June, July, and August. I can't remember. But you look at it and it'll give you that value. And that's the value you use for ambience outside. Indoors, you got to use what the condition is based on being there. Okay, if it goes to a boiler room, you got to do that and determine the temperature there. Engineers generally will do that, but electrician has to be aware of that. If the engineer is not aware of the temperatures that can be achieved in here, then you have to make that. I will venture to say that majority of the people ignore an ambient correction when it goes to a building. I would say the majority don't even take it into consideration. It needs to be, but I'm sure they don't. Now, we always generally take the adjustment factors because we can see how many conductors. But when an inspector comes in its new job and we're getting ready to release it and get their CO, it might not be all running up to capacity, and they don't know the ambient temperature that's in that room. So it might be up to the inspector to actually say, I need from the engineer the determined ambient temperature for this room. And that way we can assume that if you give me that you did all the adjustment and corrections based on that, based on the number of conductors in the raceway or cable and the actual ambient temperature in this location. We're going to hope that's how you do it. Okay. All right, let's go back to the graphic and really look at the graphic here. So here's what the code says. Where raceways or cables are exposed to direct sunlight, so that's important. If it's not direct sunlight, I guess the rule for the adder here wouldn't apply. On or above rooftops. Raceways or cables shall be installed a minimum distance from above the roof. Minimum distance above the roof to the bottom of the raceway or cable, which is basically going to be 7/8 of an inch. Now, where the distance above the roof to the bottom of the raceway is actually less than 7/8 of an inch, that's the general rule here. So we're getting into where it's less than 7/8 of an inch. A temperature adder of 33 degrees C or 60 degrees Fahrenheit have to be added to the outdoor temperature to determine the applicable ambient temperature for application of the correction factors in 31015B2A. Okay? All right, so let's kind of understand here. This adder, I've still got an ambient temperature. I still have to know what that ambient temperature is. We got to do everything that we've done up to this point. Wherever that raceway or cable is located, we have to apply an ambient. The only thing that says here is, oh, wait a minute, you installed it lower than 7/8 of an inch, or you even laid it on the roof. If that's the case, well, you're going to have to add additional temperatures. They're called adders to it. 60 degrees C or 33 degrees Fahrenheit. No, 60 degrees Fahrenheit, 33 degrees Celsius. You have to add that, depending on what you're using. You have to add that to that ambient temperature. And then you're going to go to that table we've been practicing with already, 31015 B2A. Then you go to that table. Then you pick it based on the insulation that you're using, 90 degrees C, and you select it there. Now keep in mind, if you were using an insulation that's less than 90, then you're going to use the 75 or the 60, depending on your insulation rating of your conductor. Just keep that in mind. For all of our examples, we're using 90, and that's probably the easiest example to use. All right, so let's go back and looky here. Now, there is an exception to the rule. The exception says, hey, now, if you want to forget this adder, then install XHHW-2 insulated conductors, and you don't have to apply the adder. Now, you still have the ambient. That's not going away. This exception only applies to the adder. This doesn't apply to the ambient required in 31015B2A. Okay, this is just here. Now, so what does that mean? If I install this raceway right here on the roof, then I can install XHHW-2 inside of it, and I still got the ambient to do, but I don't have to worry about this additional 33C or this 60 degree Fahrenheit. I don't have to worry about it. I can throw it out. Now, I can tell you how this came about, just briefly, is that during the development cycle in 14, which the table was a lot more complex, this whole thing came about, and in 17 kind of clarified a little bit. But what they found was that the ambient temperatures, depending on how far you are from the rooftop, you had the radiant heat that comes up from the rooftop, and you had to make that adjustment because it could rapidly raise up the temperature inside the raceway to violate the listing of the insulation. Well, since during that proposal, when it came in back in 2014, when it first got in, the presentation included an exception for XHHW-2, which is a thermal set. And as we might have talked about, thermoplastic like THHN, THWN, the insulation can be reformed. It can be remolded. If it gets too hot, it can deform. That's why we have to build these protections in here. But with thermoset, it doesn't have a good melting point. It's very high. In fact, it gets into crystalline form before it gets into a full melting point. In fact, we as a manufacturer at Encore Wire, we can't even take thermoset and remelt it and reuse it. We grind it and use it for other things like fillers, but we can't reuse it because it doesn't melt. It's a cross-linked application, and those molecules get cross-linked and they become very resilient and they don't reform or remelt very easily. So that leads itself to understand why it's better product for a hot environment. Okay. Now, still don't lose sight of the fact that it's 90 degree rated insulation. So don't think you get any benefit from that. Yeah, it won't deform like THHN, but you still can't, it's still 90 degrees C. So whether you choose THHN/THWN-2 or XHHW-2, it doesn't matter. The only benefit here is that if it's less than 7/8 of an inch, if it was THHN/THWN-2, then I'd have to apply the adder. If it's XHHW-2, then I can still do the ambient, but I get to forget about the little adder. I don't have to worry about it. Okay, so that's how that applies. Now this is dramatically different, again, than it was in the 14 code, which had a bunch of different heights on here. And it could get complicated. Here it's pretty easy. Again, you're going to get that outdoor ambient temperature from the ASHRAE Handbook Fundamentals, or you're going to go to copper.org. That's COPPER.org. And you're going to go to the search feature. You're going to type rooftops, and you should be able to find that on that website. If you do not find it, email me at info@masterthenec.com, and I will see that you get a copy. All right, so let's see how this impacts it. So in this case, we went to that little guide, the Copper Development Association guide, or to the ASHRAE, and it said that the area that I'm in is 98 degrees Fahrenheit. So that's my ambient. So that's my starting point. Now, my raceway is less than 7/8 inch above the rooftop, and it is in direct sunlight. Oh, goody goody. Now, I don't have more than 3 current carrying conductors, so I don't have an adjustment to make. I'm just going to do ambience and the adder here. So I take my 98 degrees Fahrenheit, and then I have to apply my adder as we've talked about. And that adder is 60 degrees. Since I'm dealing in Fahrenheit, if I was dealing in Celsius, it would be 33 degrees Celsius, but I'm dealing in Fahrenheit here. So that results at 158 degrees Fahrenheit. So I do exactly what I did before. I go over to 31015B2A. I go to the 90 degree column because we are dealing with a THHN, THWN-2. These are 90 degree wet or dry. I go down, and in that column under the 158 degrees Fahrenheit, you'll see that it has a percentage of 58%. Now we convert that to a decimal, 0.58. Now, in our case here, we looked at the nameplate. And we already started in our example, which says we had a 4. But you have a nameplate rating on here. And most of the nameplate ratings on the air conditioning units, for example, will say a maximum overcurrent device and minimum circuit ampacity for sizing conductors, and then maximum for the overcurrent device. And you generally follow those rules. And they're all governed in 440 of the NEC, where we get those rules from. It's just the manufacturers will put this on a nameplate for you to be able to use. And so you get those values. So we're going to assume here that they did that and they selected a 4. Now they want to make sure that their 4 has enough ampacity after the application of this ambient correction and the adder that's applied. So we'll go back to this and look. So in this case, we had a 4 gauge under the 90 degree C column in 31015B16. It's good for 95 amperes. And we could validate that, but we already know that's the case. And then it says, okay, so now I'm multiplying because I want to go down and make sure that at that point I've got enough to handle whatever the load is. And I don't know the load. So if this was an exam question, all it wants to know is what is the ampacity of this conductor after the applications of an adjustment, after the application of a correction and a corrective adder. Okay, so 95 amps times 0.58 is 55.1 amperes is the allowable ampacity of the 4 AWG copper. Now, depending on the exam you're taking, I have seen this. It might be an answer might be 55.1 or it might be 55. The absolute answer is 55.1. However, you might only see the answer of 55. And again, 0.1, you're able to drop down from that if you want. But you got to remember, ampacity of conductor is the ampacity of conductor. So the true ampacity of the conductor is actually at this point 55.1. So I would kind of steer towards the 55.1. But I'm just telling you that in case you get on an exam and there's a 55.1, but there's no 55, then I would go with that. If there is a 55 but no 55.1, then I would go with the 55. Now let's see how this impacts us if we had done this differently. Let's say that we installed the same raceway, but we were at least 7/8 of an inch. And if that's the case, then we only had to take into consideration this 98 degrees Fahrenheit. So at that point, we go back to the 4 gauge in the 90 degree column. We do the 95 amps times 0.91, and that results in an 86.45 amperes. Okay, so that 4 has a lot more current carrying capacity on it than it did when I had to apply that adder. In fact, it's 31 amps or 31.35 amps difference. That is huge. So you have to take that into consideration because ultimately I could have selected a 4, but after I apply the actual correction for the ambient, which was 98 degrees, plus the adder of 60 degrees F, I might have a conductor now that actually can't handle the load, which is going to result in me having to move to a larger size conductor. Okay. Now let's look at some other variables here. Let's look at 31015B3A1. Okay, this is dealing with cable trays. Now we're not going to get into cable trays, and let me bring you back here. Cable trays can be complex. What we're assuming here is that you installed that cable tray. It's the number of conductors, the layers, the cable tray type, and all of that was in compliance with 392.22a. Assuming that you did all that, the ampacity values that are found in 31015B16 can apply, okay? Assuming that you had an installation that was compliant with 392.22a, okay? We're not going to go with all those because that is a detailed presentation, and I don't want to go into that detail in this presentation because we're really trying to learn the basics. If I go into cable trays and I go into conductor ampacities and that, it could get confusing. I will have another advanced adjustment and correction video that will actually explain those. But again, for exam prep, you're generally not going to get those values. You're going to get the values that we're discussing here. So, but I wanted to talk about it. Now, the ampacity values, which can be altered in 392.80. Now, that has a lot to do with a compliance with 392.22a. So keep that in mind. We're not going to go over those because the ampacities in 392.80 might have to do with the spacing, the number of conductors, and the application of a percentage lower than what's in 310.15b16. So you have to keep all those things in mind. This presentation, we're not getting into those right now. But I did want to make you aware of it. That's what this one deals with. Okay. Now, again, it assumes that you follow all the rules in 392.22a. If that's the case, and that has to do with the conductors, the sizes, the parameters, the cable tray systems, whether it's solid bottom, ladder style, or whatever it is, you can actually use 310.15b16 ampacities for that, okay, for those calculations. Now, the presentation will not be going over the rules that are found in 392.80, which we just talked about, which also have other parameters, and it could actually give you a percentage that you can exceed when you're meeting some of these conditions of installation in cable trays. And we're not going to cover that in this presentation. The next one we're going to talk about is 310.15b3a2, which is the ampacity, the adjustment factors shall not apply to conductors and raceways having a length not exceeding 24 inches. So this is the nipple rule. So if I have a nipple that's 24 inches or less, or a raceway, it's still a raceway, that's 24 inches or less, or it could be a cable that's 24 inches or less, then I don't have to apply the adjustment. Okay, we're in the adjustment now. Anything you see that's in 310.15b3 is going to be dealing with the adjustment. Now, could I have an ambient correction applied here? Sure. I could have an elevated ambient temperature that I have to account for. But do I have to apply the adjustment on those small 24 inches and less? No. So I get to get away from doing that. So I get a little allowance there for that. All right. The next one is a great rule. This is 310.15a2, and it is selection of ampacity. And let me kind of set the tone here real quick. So this is a neat rule. So let's say I'm in a building and I'm running from point A to point B. And somewhere along the way, I'm going to be running a portion of my raceway through an area that's going to have a more elevated ambient temperature than most of the other parts of the run. Maybe it's running through the boiler room. I'm trying to get from point A to point B, and I got to go through this room that it's going to have a little higher ambience. Well, I have to do a calculation on both locations based on the ambient temperatures, the number of conductors, everything else, and I want to come up with an ampacity value. Ultimately, I got to choose a conductor based on that. But what I want to do is I want to choose the value for the higher ampacity value, or wherever the actual lower ambient temperature was at. I don't want to have to be bogged down by that area where the ambient temperature is so high. So the code gives me this rule and says, look, if the portion of that run is the one that's going to result in the lower ampacity, means it has a higher temperature, that area is not more than 10% or 10 feet, whichever is lesser, of the entire run, then I get to discount that lower ampacity value and simply take the higher value, which is what we want to do, okay? So that's what this rule covers. Now, this can be a lifesaver if you're dealing with SE cable that's running against thermal insulation for a small portion or penetrating a wall, or if you have raceways that are going up and through an area where it's might be going through something that's going to change the ambient temperature, and you're like, oh. So you really need to know that distance to see whether or not it's 10% or 10 feet, whichever the lesser of the two, of that total run, so that I can simply discount or throw away that portion that could result in a lower ampacity because of that elevated heat, okay? That's important. So let's look at the graphic. It kind of lays it out. So I've got a conductor here, and this conductor running 100 feet. Now, it's not in a raceway. We're just talking conductor here. 100 feet. Now, 10% of this 100 feet is 10 feet, or 10 feet. I said that wrong. All right, 10% of 100 feet is 10 feet. And actually, it matches the same 10 feet. So both of this are lesser. It's the lesser of 10 foot or 10%. Well, both of them actually are the same. So if the lower ampacity resulted due to an adjustment and correction right here, but the rest of, or 90 feet of this run, didn't have the same high elevated ambient temperature, and so my ampacity was a little higher, I can use this for the entire run. I can discount this. Now, this rule is real important as well when you're in enclosures and you're trying to come out of enclosures. And you say you have a surface mounted enclosure, you have that rule that allows us to be able to run conductors up through a small portion of raceway up into the ceiling area. That the key is inside the enclosure, you might be bundling all these conductors together. Well, at this point, this rule would allow you to ignore the effects of the bundling that would take place because the length is not more than 10% or 10 feet, whichever is the lesser of the two, for the overall run. And that might save you in an application. Okay, I know that it has saved many people when you're dealing with SE cable, where it goes up through an attic into the insulation and then down to its load, or maybe up to an air handler unit. And so the portion that's in contact, as it results in a different ampacity, then what happens is I can use the area that has the higher ampacity value than the lower value, and I get to discount the lower and throw it out and use the higher. That's saved people in all kinds of applications before. So just know that it's there. Now, I should mention the general rule, however, is if this wasn't the case, if you weren't able to apply here, and this was more than 10 feet or 10%, then you have to follow the general rule. And the general rule is I got to go by the lower value because this is the weakest link. I can't protect it here at this higher value when I've got a lower value. And the concept behind that is 10 foot or 10% is going to be enough to utilize the conductor and this side of it as a heat sink and pull away the heat. And this side at the termination to help pull away heat. Everything works together and you don't have a problem, okay? Now, if this was in the middle of a run, then I might have a conductor on either side that's at a higher ampacity because it doesn't have as bad temperatures. Then this conductor is going to have that excess heat pulled away on both sides of this location, and that's going to be sucked away or act like a heat sink, and that's going to be beneficial to the conductor itself. All right, this next one is 310.15B3A3. Now let me kind of give you the lowdown on this one because we can run through this one pretty quick because I don't really have a graphic for it. When I'm running underground raceway and I'm coming in a moment I'm going to go from a horizontal to a vertical and I'm entering and leaving out of the ground, if I run, as long as I don't exceed 10 feet or more than 4 conductors in the raceway, and it's of a specific type of raceway, and we'll look at that in a second, then I can discount the actual adjustment because I am over 3 current carrying conductors. I'm at 4. Okay. But as long as I don't exceed 4 conductors, then I don't have to apply the adjustment. Now, the ambient might apply, above ground might apply, but I don't have to apply the adjustment. But it has to be with 4 type of raceways that this applies. So let's look at those. So this rule says that if I use rigid metal conduit, intermediate conduit, PVC, doesn't say whether it's schedule 40 or 80, although I will tell you that the rule says with these conductors are protected, have physical protection, and generally that would be, as it comes out of the ground, that would be schedule 80. The part in the ground could be 40. But at any rate, it does say RMC, INC, PVC, or RTRC, which I've never dealt with that, and that is reinforced thermal setting resin conduit. I've never even seen it. So, but as long as you're using any one of these wiring methods here, or these raceways, I should actually say, when you finally turn those raceways toward the vertical and come out of the ground, if the length isn't more than 10 feet and the conductors inside the raceway are not more than 4, then no adjustment factor is applying. Remember, you might have an ambient, but you don't have an adjustment. Don't get the two confused. Now let's talk about MC cable. So under 310.15 B3A4 for MC and AC cable, let's say I don't want to apply an adjustment factor. Well, if I meet all the rules here, A, B, C, and D, then I don't have to apply an adjustment factor. But I still have an ambient if it's depending on the temperature these are located in. But we're just trying to see what kind of rule allows us to not have to apply an adjustment factor. Well, first of all, if your MCs or AC cables don't have an overall outer jacket, like a PVC jacketing, okay. If they don't, then that's A, and you're good. B, it says each cable has not more than 3 current carrying conductors. Well, in this example right here, I've got a blue, a black, a red, and a white. Now, if this white wasn't a current carrying conductor, and we discussed that earlier, then I would only have 3 current carrying conductors, and I would be in compliance. So this cable would be good, this cable would be good, and everybody would be good. Now, incidentally, if this was a current carrying conductor, as we talked about earlier, then I would have 1, 2, 3, 4. And of course, then this allowance to omit an adjustment factor wouldn't apply, and I'd have to apply an adjustment factor for the number of current carrying conductors just like I would any other time. Just like I would if it was a normal raceway. Okay? But this is a cable assembly. So, in this case, I don't have it. I've got only 3 current carrying conductors because that neutral is not a current carrying conductor. C, the conductors are 12 AWG copper. Okay? Copper. Not aluminum, copper. And they're not smaller or larger than 12. If my calculation or whatever I'm doing results in a conductor that's larger than 12, then this rule doesn't apply, and I have to apply the adjustment factors based on the number of current carrying conductors here. But in this case, they are 12 gauge. There isn't more than 3 in each cable. They aren't PVC jacketed, so I'm good to go. I'm almost ready to say I don't have to apply any adjustment factor. Next, I get to D. D says not more than 20 current carrying conductors are installed without maintaining spacing. They're stacked or are supported on bridle rings. All right, obviously these are stacked. They're right side by side. There is no spacing in them. They're right next to each other. As long as I don't have more than 20 current carrying conductors, then, and I meet all these other rules, then I simply do not have to apply an adjustment factor. Now, what happens if I meet all these rules, A, B, and C, but I end up with more than 20 current carrying conductors? Then the code has an exception and it says, okay, look, if I meet the rules of A, B, and C, means that there are no PVC jacket, there's no more than 3 current carrying conductors, and the size is a 12 gauge copper. Well, what we'll do is we'll let you, and the cables are installed in no more than 20 current. Let's read this again because I just got myself confused. If cables meeting the requirements of 31015 B34A through C, which we talked about here, with more than 20 current carrying conductors are installed longer than 24 inches without maintaining spacing, kind of same we said here, or stacking, or are supported on bridle rings, a 60% adjustment factor shall be applied. Okay. So, it can get confusing when you read all these codes. So, we know that in a regular raceway, when we had these conductors and we had 4 to 6, and we had 80% adjustment, we had 7 to 9, we have a 70%. We have all those. What this is saying is, okay, if you meet A, B, and C, and you have over 20 current carrying conductors based on bundling for 24 inches and more, but you met all the other rules, we'll let you do it, but you're going to apply a flat 0.60 or 60% adjustment factor. No more than that, no less than that. Let you apply 60. And that's what you apply. So that's what it's saying here. If any one of the A, B, C doesn't apply, or to whatever your installation is or what you're doing, then you can't apply, you got to add an adjustment factor. You can't get away with not applying one. So this rule here means you have to meet all of the rules, and we do give you an exception for when you have more than 20 current carrying conductors, but the only exception is saying, okay, you got to do an ampacity adjustment at 60%. You don't have to worry about all those tables in 31015, B3A. Just go right to 60% and apply it, and there you go, okay? Whereas normally, if we met all these rules, we wouldn't have to apply any adjustment. Again, still have an ambient we might have to apply, but no adjustment. Remember, 2 different things here. Ambient is a correction, and adjustment is for the number of current carrying conductors in the raceway. I think you get it. All right. Now let's put the 2 together and do an application in real world. In this case, we're going to use 39 amperes. We're going to try to put everything we've learned together so far together. So we have 39 amps of continuous load. We have an EMT tubing. We got 6 current carrying conductors, THHN, THWN-2, copper. Dry location. Not that it would matter here because it is THHN, THWN-2. And the terminals are rated at 75 degrees C, and we have an ambient temperature of 40 degrees C. Now, since it is a continuous load, we have to choose the larger of 210.19A1A versus 210.19A1B. So if you look at A, you actually take 35 amperes. Actually, that's wrong because we're dealing with 39 amperes. So let's come back to me and do this because actually the graphic is wrong. Should have looked at that before I got into it. We got to make sure we change that before we put the book. So it's 39 times 1.25. That's 48.75 amperes. Okay, so that is a continuous load application for the A1A. So we write that down. So we have to find a conductor under the 75-degree column that can handle 48.75 amperes. So let's go to the code, and we gotta get there now. So we're in the code. We're all the way back here. So now we need to go all the way to 310.15B16. And I'm going to draw it all the way down. Again, sorry, I don't have my tabs up to be able to jump down to it. We're just going to kind of scroll down to it a little bit. And again, our conductor was at the 48.75 amperes. So under the 75-degree column, because we haven't applied any adjustment corrections, because that's not what 210.19A1A is all about. It says simply follow the terminals. So I go down here, and it looks like, okay, an 8 gauge. Okay, so an 8 gauge is good for 50. Okay, so it looks like I'm okay. As far as sizing conductor, that looks like we're good first. All right, so let's go back to the presentation. All right, so it looks like we're good at an 8 so far. Now, we're at 39 amps, so now we have to compare it to B. We had an 8 gauge, we were good. Now, B says this. We have to take the actual load, which was 39 amps. We don't have to take into account the 25% for continuous load in this rule, remember. And we have the 0.80, which is under 310.15B3A. That's dealing with the 6 current carrying conductors. So we got the 80. And then we have the ambient of 40 degrees C, which is dealing with 310.15B2A, okay, which is 0.91. If we went to that table, that's where we'd get that. And so what we do is we're trying to go up now, we're dividing, and we need to see what conductor we have to pull from the 90-degree column. And that is 39 divided by 0.80 divided by 0.91 equals 53.57 amperes. All right, so I need a conductor that's good for 53.57 amperes. All right, so we got to go to the code, 53.57. So we were at 8 last time, so let's just see if the 8 still works. Okay. All right. So there it looks like 55. So if we look at our example, we were at 53.57. So it looks like we're saying, oh, okay, well, it looks like an 8's going to work. 8's not a problem. However, we now have to apply the conditions of use here that we didn't have to apply before. So let's go back and see what we're doing. And remember, we still haven't looked at the overcurrent device yet. So now let's go back and we go, okay, we have 53.57 amps. An 8 gauge is good for 55. Everything looks good. It looks like we're still in the 8. All right. But we haven't applied the adjustment and correction factors now. We only started from the 8. So if we take that 55 amps times 0.80 times 0.91, because we were in the 8 gauge, we result in a 40.04 amp rated conductor. Now, can that 40.04 amps handle the 49 amps of actual maximum load? The answer is absolutely 100% yes. Does it violate the ratings of the 75-degree terminals? No. However, at this point, you're an electrician and you're thinking, I sized it for the adjustment. I sized it for the correction. I'm good. It's an 8. Now I have to protect that conductor at its ampacity. The ampacity of that conductor now is good at 40 amperes, 40.04. That's what its ampacity is. So at this point, I got a problem. And another thing we want to look at, let's go back real quick. Let's look at this because I want to show you something. Since these conductors resulted in the same size, if you look at the difference in the two, back in this application, it was 125%, which was 48. I don't know where this 44 came from. It was 48.75, okay, which is the same conductor, but it is larger in ampacity. So it would have to still be on a 50, right? 48. Whereas this one resulted in a conductor that's good for 40.04, right? However, because we're using this one as the adjustment corrections and resulted in a larger conductor, we now have the conductor that has to protect it at its ampacity. In this case, the new ampacity from the 90 degree C is only good for 40.04 amperes. Okay. Now, an 8 AWG can handle the actual load as described in 210.19A1B, but based on the rules of 210.20A, the overcurrent device cannot be less than 125% of the actual load times 125%, which in this case was 48.79 amps, which is 49 amps. Well, I cannot protect a conductor that's good for 40 amps on a 50 amp overcurrent device. Remember, because we don't make one at 49, we got to go to 50. So the rule would be that I'd have to protect it, you would think, at the next size up, or of above 40 would be a 45 ampere. However, the rule said that it can't be less than 125% of the actual load times 125% of the actual load. That forced me to have a 50 amp overcurrent device. Well, that 8 gauge is not going to work. At that point, I have to drop down to a 6 gauge. And if I do the calculation from the 6 gauge at the 90, it's 75 amperes times 0.8 times 0.91, gives me a conductor that's good for 54.6 amperes. The 54.6 amperes doesn't exceed the 75 degree value per 110.14c1. So the 6 can clearly handle the 39 amps of load, the actual load, okay? And it's perfectly acceptable to put a conductor that has a capacity of 54.6 amperes. Again, I'm not using that 54.6 amperes. I'm just using a conductor that actually has the ability to have that. But I'm terminating it on a 50 amp overcurrent device, and the code allows me to do that. So when you compare the two of 210.19a1a and 210.19a1b, you choose the larger conductor that results in the calculation. In this case, the overcurrent device is the one that's going to be the ruling factor here, and it's going to require it to be a 6 gauge because I have to terminate that conductor on a overcurrent device that it's at least 125% of the continuous load. And that's how we jumped it into a 6, okay? So an 8 was good until we started applying these adjustment and corrections, and then we had to deal with that, okay? All right, let's move on. So let's talk about the conversion. A derating would be completely useless if we discuss the allowances provided in 310.15b7. So now we're getting into that D7 where we had that little mini table that's in the back of the code book. It's now in example D7. Now, if you're not familiar with this table, you must be pretty new to the industry because the table disappeared in the 2014 code. So that would tell me you came into the 14 codes. Because prior to that, at 310.15b7, we had this little table. Now, the first things first, we need to look at what the table applies to. It says, now 310.15b7 says, single-phase dwelling services and feeders for one-family dwellings and the individual dwelling units of a two-family and multifamily dwellings, that'd be like apartment complexes. The service and feeder conductor is supplied by a single-phase 120-240 volt system shall be permitted to be sized in accordance with 310.15b7 1 through 4. Now this right here just happens to be a normal, typical 120-240 volt transformer that generally supplies the applications that we're talking about for a 1 and 2 family or an individual dwelling unit of a 2-family building or a multifamily dwelling. Okay, so that's what this is generally right here. Now, the code changed and said, well, wait a minute. Let's also say that for a 1-family dwelling and the individual dwelling units of a 2-family and multifamily dwelling, a single-phase feeder conductor consisting of 2 ungrounded conductors and the neutral conductor from a 208 120 volt system shall be permitted to be sized according to 310.15b7 1 through 3. Okay, so in that application, I am able to use the calculation here. Now, again, this used to be, and I guess I should bring you back to me. This used to be a little table that was based on, used to be an old rule where it's 84% of the values that are in 310.15b16. But they decided to use 83% for the 2014 cycle where this came about, and they started to use a calculation. Now, a lot of people say they've made this confusing because they should have just left the table in. The problem is the table before didn't kind of lend itself to have to apply any adjustment and corrections. People thought you could just go right to that table, whatever it was. If the service rating was 175, you pull the conductor from that table and you're done. Even if you had an adjustment or correction, it didn't apply. That was the farthest thing from the truth. You still had to apply adjustment and corrections. It just didn't say it really well. So now it does, because it gives you a calculation, which is going to kind of tell you that's like any other calculation. I have to apply some adjustment and corrections. So that's where we're at on that. So let's go back and look at it. So in this case, it says, note that this does not permit 31015B74 to be used because the neutral in those systems, depending on the conditions of installation, you have nonlinear loads and whatnot, could affect the reduced size grounded neutral conductor. Again, you could have a neutral that can't be reduced. So it does give you some allowances, but you'll notice right here that when it's dealing with 208-120, it's telling you that it's okay to use the table, but it only allows you to use 1 through 3. It doesn't let you use 4. Whereas up here in 122/40 volt systems, it lets you use it for B7 1 through 4. Okay, so just remember that. And that's the reason right there. So let's look at this graphic. And this graphic, again, we're gonna do the rules here in 31015B7. We clearly understand the components of the rule. Many folks panicked when they removed that 2014 table. All right, but again, don't worry, the table's back there again in Informative Annex D7. And I guess, and I don't know what's happening in the 2017 cycle for that. I know they're doing a complete rewrite, or I don't know if it'll pass or we'll all agree on it, but they're doing a total rewrite of Article 310 to try to make it a little easier to understand. I can't give you any more than that because I don't sit on that code making panel. I sit on code making panel 5 and I sit on code making panel 17. Don't get me started about 17, buddy. But anyway, I sit on those two panels, right? But this panel, which is code making panel 6, it's kind of rewriting. And there's been a combination of 6 and 7 now, so there's just one panel. And they cover all of the wiring methods that are covered, previously were covered in code making panel 7, but also the ones that are in 6. So there's been a consolidation, if you will, and they've been brought together. So they're redoing this. To my counterparts in other wiring cable manufacturers got together, and they're actually working on that. And I expect it to be some great work. Those are great individuals, and I expect them to put some good work together for all of us to review when it comes to Hilton Head in January of 2018. And depending on when you're watching this video, it might have already happened. Okay, then I got to do another video to explain 310 all over again, right? All right, so let's go back. All right, so this graphic I came up with to depict it. Now, again, remember, this rule only applies to services, and this is B7.1, because there's 4 of them, but we're going to do each one of them. In B7.1, we're only dealing with services, and it only deals with services rated 100 through 400 amperes. No, it doesn't apply to those over 400 amperes. It only applies here. It says the service conductor supplying the entire load associated with the one-family dwelling, or the service conductor supplying the entire load associated with an individual dwelling unit in a 2-family or a multifamily dwelling, shall be permitted to have the ampacity, this is the conductors, if you will, rated not less than 83% of the service rating. Okay, so these are the service conductors. Here's your service conductors coming in. In this case, it looks like they're service conductors overhead. And they're coming in, they're going through the meter, and they're coming over, and they're going here, here. So this conductor size based on the service rating. Again, let's say this service rating was 175 amp service rating. And we are using the same example that's in Annex D of the NEC to make it easy to understand. So in that case, it's just really simple math. I have to make sure that these conductors are at least no less than 83% of the service rating. So in this case, you just simply take the 175 times 0.83, that represents the 83%, and it's 145.25 amperes. So you visit 31015B16, and you choose a conductor from the appropriate terminal rating under the 60 or 75, and chances are this is probably going to be 75. And you simply select the conductor from that column because we haven't applied any adjustment and corrections here. We are simply just choosing from the columns. And in that case, you go down to 75 because we expressed in most of our calculations that our lugs are 75 degrees C. So it would be a 1-aught copper or a 3-aught aluminum. And all I say is aught all the time, but it's actually not. But anyway, 1-aught and 3-aught. All right, now, over here, you'll notice that I don't show any grounding electrode systems because it really doesn't bring any clarity to the graphic. We're just simply showing you that this conductor right here has to be a minimum 83%. Now, of the rating of the service. Now, another thing I will throw out there, this has to handle 100% of the load. If I had a panel right here, or I had something where there was actually loads were taken out before it got to this panel, then I can't apply this rule, and I just have to size it based on 31015B16 like I do for anything else. Okay, so to use this table, I have to supply 100% of the loads over here. Okay, and this is for the service application. All right, again, 100% of the load. Now let's look at this one, because this one tends to be the one most people fall into. Now this one is 31015B7-2. Now this is dealing with feeders. Now again, we're dealing with 100 through 400 amperes. If it's under 100, you calculate it as you would normally. If it's over 400, you calculate it as you would normally using 31015B16 and apply all the adjustment and corrections necessary. Under this rule here, it says a feeder conductor supplying the entire load associated with a one-family dwelling. That'd be like your house. Or the feeder conductor supplying the entire load associated with an individual dwelling unit. This might be an individual dwelling in an apartment complex. Or I guess it could be a two-family or a multifamily dwelling. Shall be permitted to have an ampacity. Again, you could size it under the normal 31015B16 if you want. This is allowing you to size it based on not less than 83% of the feeder rating. So whatever the rating is here, in this case, we'll stick with the 75 rating amps. So here's your meters over here. We don't show the meter to the right. It comes in to the service equipment. And it's coming in and it's coming here. And then this is simply just a disconnect, service disconnect. Okay, it is providing overload protection for these conductors. It's providing short circuit ground fault protection as well as overload for these conductors. These are the feeders. And it comes out and it's feeding this RDP or this remote distribution panel. Okay, over here. And of course, you see that we got the grounds and the neutrals all separated over here. Here, they're all tied together. I have a great grounding and bonding video that explains everything you need to know about service side bonding and grounding, of enclosures and whatever, and raceways and all. Okay, but that's, I digress. So this feeder right here is no less than 83%. So you do the same thing. 175 times 0.83, 145.25 amps. Again, we're not applying any adjustment and corrections, so we simply go to whatever the terminals are. In the case here, they'd be 75 degrees C. I go to that column, I go down, and I find me a conductor that's going to handle 145.25 amps. And in that case, it's a 1-aught, and we can verify that, 142, by going over here to the NEC. And when we go to the NEC, we got a 1-aught, which is good for 150. So it easily can handle the 145. No problem. Now, we get a little trickier. But nothing changes. Same rules we've always applied. Oh, I should also tell you, this has to handle 100. These feeders have to handle 100% of the load. Okay? If I go from here to a panel, that's fine because the load's actually, starting here. If I had a panel over here where this single is right now, and it actually had a panel here and it had a couple breakers in here, and let's say that first service disconnect there was actually outside and it had a couple breakers underneath it. And let's say, the air conditioning unit's right here. I just want to drop out of it and feed that air conditioning unit. Well, that feeder is not seeing 100% of the load to that remote distribution panel. Okay. It's some loads. Now, a lot of you would think, well, it's seeing less loads because the loads are up ahead of it. It's just not how it works when it comes to diversity. We need all the advantages of diversity when it comes to canceling out and different things when it comes to the current. So if that panel or those feeders are not seeing 100% of the load, then this rule can't apply. And you have to size it based on the normal rules in 31015B16 when you're sizing conductors and apply adjustment and corrections and what have you. Okay. This panel has to handle 100% of load. In this example here, it is handling 100% of the load. Okay. So we want to make sure you understand that. So if there were any breakers over here other than the main breaker that's coming off and let's say feeding an air conditioning unit or whatever, or this is another panel, and I want to use the rules here in 31015B7-2 for this feeder sizing, I couldn't do it. Okay. This feeder has to handle 100% of the load. And there's your right here. 100% of the load is being supplied here. All right. So now let's look at an application here for the service where we're going to apply some kind of ambient correction. Now, we're probably not going to have an adjustment here in this application, never, because we're not going to have more than 3 current carrying conductors. Okay, but we will most likely have an ambient. So let's see what we do here. So we did this before. We did 175 amps. That's the rating. And incidentally, this applies whether it's a feeder or service, okay? It doesn't matter. 145.25 amperes. All right, and we already did that. We determined we needed a 1/0 copper or 3/0 aluminum. However, now that we have a 40 degrees C application, in this case, 90 degrees C terminals can be used for adjustment and correction. So what we do is we got to find a conductor under the 90 degrees C that can handle the actual load, which service rating, okay, which is, well, we need one that's going to handle the 145.25 amps. That's actually what we have, because we're still trying to maintain the 83%. Okay, that's what we're doing here. So we're going to go and find a conductor. So let's see, since we can use the 90 for adjustment and corrections here, we need to find a conductor that's good for 145.25 amps, okay? And you're asking me, why didn't we use this? Because this is a service rating. We're using it because we want to make sure that we have a conductor after the adjustment or correction that it's still 83% of the 175 rating, okay? That's why we do that. So that's why we're using this one. So 145.25, let's go to the code, and 145.25, and let's see what we got. So I'm in 90 degrees C because I'm doing adjustment and correction here, in this case a correction. And let's see, and I totally forgot what it was, so let me look back, and it was 145.25. Okay, so 145.25, well, 145, I need one at least 145.25. So I'm going to go up to this 1/0, and it's good for 170. Okay, so I'm at that. Okay, because I got to have at least, that. So I'm going to do that. So now let's go back. So that's a 1/0. Let's go back to the calculation here. So I know that it's 1/0. It's good for 170 under the 90. Now I want to apply the adjustment, the correction because of ambience to this conductor and see that it's still going to be okay, or at least it's still going to be good for 83%. So I take that 170 and I multiply it times 0.91 because that is what the ambient is when we go look at 31015 B2A for the 40 degrees C, and it was a 91% or 0.91. Ultimately, that gives me a conductor that's good for 194.7 amps. Well, it exceeds 145.25, which was truly 83% of this service rating or this feeder rating. So as long as I'm higher than the 145.25, I'm good to go. So it meets the minimum of 83%. It can handle the ambient temperature. And so it should be a 1/0. Now, I will tell you this. If you go look at the example D7 in the NEC handbook, or in the code, I guess, you're going to see that it says 2/0. That is incorrect. It is supposed to be a 1/0. And this is the reason. Trust me, this will get changed. I have made NFPA aware of it. I have made Code Panel 6 aware of it. It will get changed. Now, how they change that in order to make it meet the 2/0, because we want to give you another option here instead of it all being the same as the 1/0 before you did the calculation. So we might see that the ambient's going to be increased to 0.82. And if you do that math, it's going to result in a 2/0, and that way the actual calculation works out. But incidentally, in this case, since we're only doing a small correction here, the 1/0 CU would have been okay as well in this application, even with the ambient temperature of 40 degrees C. Okay, now, between me and you, let me bring it back to me and you. Between me and you, since I work for a company that makes wire, if you want to go to the 2/0 already, go for it. If you want to put 3/0 on it and just follow 31015B16 for copper, go for it. You can go bigger. Just make sure that it can fit on the terminals. I don't have a problem with you using more copper. I don't have a problem with you using more aluminum either. But we want, for exam prep, we want to make sure that we use the best possible answer, because that's what you're going to get when you're doing an exam, okay? All right, let's go back to the presentation and kind of round a lot of this up here. All right. Now, we want to finish out the B7.3 and, of course, B7.4. So B7.3, the first two was dealing with services, and B7.2 was dealing with feeder applications. B7.3 says, in no case shall a feeder for an individual dwelling unit be required to have an ampacity greater than that specified in B7.1 or B7.2. A good example of this would be maybe a feed-through panel that's being used where you size the conductors based on 31050 B7.1 or B7.2. And somehow you end up with a feed-through where your conductor results in possibly a larger conductor that's going out to that individual dwelling unit. Well, the code here is saying no, It does not have to be increased in size, okay? Simply size the minimum size feeder per the minimum's 83% rule and move on. Don't make B73 complicated. It's basically saying this. Whatever I size it for that feeder or that service conductor, and now if I'm going through a feed through or I'm going to another application where I'm continuing on to an individual dwelling unit, whatever I sized originally under B71 or B72, I don't have to reinvent the wheel here, okay? It doesn't have to be larger than that. Even if a calculation could result in it larger, it doesn't have to be, okay? So that's what that rule is saying. So again, size them based on B71, B72, and you're good to go. All right, no, we don't need to code. All right, let's go back to there. Now let's look at, whoops, we're not done yet. Oh, look, I blew it for y'all. Let's look at 310B74 real quick. God, did it again. It says, make sure I'm on it here because I don't want to make sure I'm lost. Look, I wanted to end this thing quick as y'all guys do. See here, so 310.15B74. We're rounding up this last one here. It says grounded conductors shall be permitted to be sized smaller than the ungrounded conductors if the requirements of 220.61, that's a sizing requirement based on the neutral load, and 230.42, which is going to refer us back to sizing at no less than 250.24c. As long as you size and do everything there, and again, when you're dealing with all of these applications, for feeders, you would be in accordance with 215.2 and again, calculations per 220.61. All right. Now, you notice that this is B74, that we weren't allowed to do this. Now, what this is basically saying in a nutshell is that you might have a case, and you are with SE cable, you do all the time, you're going to have a neutral conductor that might end up being smaller than the phase conductors. And that's okay. All right. Not a problem. What we do want to remind you that B74 can't be used when you're dealing with the feeder, and you applied earlier when we were talking about a 120-208Y or a 208Y120, that you can't do that reduction with the neutral, okay? And we saw why earlier when it talked about counting a neutral as a current carrying conductor, okay? You're permitted to use this, but you can't reduce it. So you still have to size your neutrals in 220.61. It can't be less than 230.43. C, and ultimately it also, we have a grounding conductor sizing requirements in 250.102 C1. So there's a table there that deals with the grounded conductor minimum sizing, and you have to compare the two and make sure it's, you know, which one it's actually going to handle load, and one's the minimum size based on that table, because 230.42 and all of that is going to end up sending you up there to 250.102C1. So I think you get the point. So that's the point here. It's saying, no, you can't use it. Now, for me and you, for most calculations on exams, they're not going to give you that aspect. They're going to be 120-240 applications. They might give you an ambient adjustment just like we did. And your neutral could be smaller. But usually they're going to want you to size the conductors based on 310.15 B71 or B72 is what they're going to do for that. All right, let's go back and round this thing out. All right, now a translation, I just want to clarify here. Where applicable, the grounded conductor is calculated in accordance with 220.61. We already talked about that. And as stated in 230.4, where it states that the grounded conductor shall not be smaller than the minimum size required in 250.24c. Okay, so that's where that comes from. Not sure what I said up here. But here's where we're dealing with it here. Okay, so this is a size, and ultimately this is probably going to kick you also again to a 250.102C1 in that table, because that's the new table for sizing grounded conductors as well. And then when you're dealing with feeders, we're applicable. 215.2A2, the feeder circuit grounded conductor shall not be smaller than it's required by 250.122. Okay, so since we have an overcurrent device ahead of the feeder, it's saying, look, it can't be smaller than what would be required under 250.122 for what we would do for a equipment grounding conductor. So basically there's your rule there for a feeder, okay? So it can't be smaller than that. It might be larger than that based on whatever the calculation came up of 220.61, okay? And it also says, well, Yeah, but also under 250.122F, it shall not apply where ground and conductors are run in parallel. Okay. That's it. We made it to the end. We're only going to talk about those applications. Again, I can see it. There you go. We're at the end. Congratulations, you made it. We've covered a lot. We talked about the terminal limitations. We talked about the breakers and how important role, and we saw how that played. We looked at all the other aspects of adjustment and corrections, nipples, and you can avoid, you don't have to account for the adjustment. Still got to worry about the ambient. We talked about the MC and AC cables and when you can discount and not use an adjustment. But we also looked at it when you have to use an adjustment. And if none of those conditions apply, you've got to apply an adjustment or correction. We looked at all that. We looked at that neat rule of 31015A2, whereas we could take 10 foot or 10%, whichever the lesser of the two, of the total run, and discount the portion of the run that results in a lower ampacity due to the ambience, and take the one that has a higher ampacity and discard that lower. That can be very beneficial on SE cable and some of the other applications you might run into. Running a raceway through an ambient location, maybe it just goes through the portion of a room, a boiler room, and that small portion is not more than 10% or 10 foot, whichever the lesser of the two, then I get to discount that value there. And I could say, I don't have to worry about that elevated ambient in that location. Okay, so that's a rule that we might apply to you. So we covered all that. We showed you some examples of continuous load and non-continuous load, how you add them together. We covered all that. I'm going to encourage you that if you have any questions or you feel I didn't cover anything to good detail, I am tired. I got to the end of that. This is a one-take video. It's about 2.5 hours or so. So at the end there, I got a little, starting to have a little brain going a little bit somewhere. But I really wanted to help you out and hopefully explain a little bit on adjustment and corrections. If you have any comments, feel free to email us at info at masterthenec.com. You can also email us at info@electricalcodeacademy.com, spelled just like you see it up here, because it's over here, I guess. And you can also go to our YouTube channel and just go to YouTube and type Master the NEC, and you'll find our channel. Subscribe. Or you can go to our website at masterthenec.com.net or .org, or electricalcodeacademy.com.net or .org, and you'll see links on there to get you to Facebook, to LinkedIn, to I don't even know what else is in there. Facebook, LinkedIn, Twitter at masterthenec, but you can get there from our website. Go to our website and watch our videos. I'm not a know-it-all. Sometimes I'm like anybody else. The only difference is I don't do blooper reels. I give you what I give you. Sometimes I know what I'm talking about, but then I might say something differently. Like I might say adjustment when I'm talking about a temperature correction, or I might say adjustment when I'm, or I might say temperature correction or a correction when I'm talking about an adjustment. That's the number of current carrying conductors. I also talk really fast. And when I talk really fast, my mind doesn't catch up to my mouth. Apologize. I'm already going to apologize. Hey, I'm blessed to be able to do this. I'm blessed to work for a manufacturer that allows me to do this on my own time. I do thanks for them as well. I encourage you to look up EncoreWire.com and look at the wire and cable offerings they have. They don't sponsor this, but again, I work for them, and I am blessed that our CEO allows me to do presentations like this. Now, this module here was on derating demystified. And, we wanted to kind of break up those little things. So follow the links that are down here. Look at the scrolling bar. Visit our website. Visit YouTube. And hopefully you visit our Facebook page as well. Just go to Facebook and type in Master the NEC and you'll find us. God, that's a lot of words. God bless. Thanks for watching. I hope you learned something. Hopefully I didn't confuse anybody. Because if I did, I'm sorry. If I helped you, great. Next time, come back and visit us. God bless. And we'll move on to the next module here in our exam preparation and our NEC examination profile series.